If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. In the vast expanse of the universe, where countless stars twinkle like distant diamonds, lies one of humanity's greatest revelations: the existence of planets beyond our solar system. Known as exoplanets, these celestial bodies orbit stars other than our Sun, and their discovery has fundamentally changed how we perceive our place in the cosmos. The universe, once imagined as a static and predictable backdrop, has unfolded into a dynamic and diverse arena of worlds, each with its unique story, mysteries, and possibilities. To appreciate the profound significance of exoplanets, one must first journey back to a time when the notion of planets outside our solar system was little more than a speculative dream. For centuries, astronomers peered through rudimentary telescopes, their observations limited to the planets circling our Sun. While the idea of other planetary systems wasn't new, philosophers and thinkers had hypothesized their existence. It wasn't until the 20th century that science had the tools and methodology to validate such theories. This marked the beginning of a golden age in astronomy, driven by an insatiable curiosity to answer a simple yet profound question: are we alone? The quest to discover exoplanets was far from straightforward. Unlike stars, which emit light, planets merely reflected, making them incredibly difficult to detect. Imagine trying to spot a firefly next to a blazing spotlight from miles away. This is the challenge astronomers face when observing planets around distant stars. Yet, through ingenuity and technological advancements, these limitations were overcome, ushering in a new era of discovery. The first confirmed exoplanet detection occurred in 1992 around a pulsar, a type of dead star. This was not only unexpected but also a humbling reminder of how little we truly understood about the universe's diversity. Fast forward to today, and the number of confirmed exoplanets has soared into the thousands, with countless more awaiting verification. Each discovery adds a piece to the cosmic puzzle, revealing systems that range from eerily familiar to wildly alien. Some exoplanets are massive gas giants that dwarf Jupiter, while others are rocky Earth-like worlds that may hold the ingredients for life. Among these discoveries, scientists are not merely cataloging planets, but also seeking answers to some of humanity's oldest questions. How do planets form? Can they sustain life? And if so, what might that life look like? The search for exoplanets is not just a scientific endeavor, it's a profoundly human one. It taps into our innate desire to explore and understand. Exoplanets force us to confront the enormity of the universe and our place within it. They ignite our imagination, inspiring visions of alien landscapes and civilizations. But perhaps most importantly, they remind us that the story of the cosmos is far from complete. For every exoplanet discovered, countless more await, hidden in the shadows, waiting to be unveiled. In this chapter, we will delve deeper into the origins and significance of exoplanetary research. From the earliest hypotheses to the technological breakthroughs that made detection possible, we will explore how these distant worlds have reshaped our understanding of the universe. We will also examine the implications of these discoveries, not just for science, but for humanity's collective imagination. What do exoplanets tell us about the likelihood of life elsewhere? How do they challenge our understanding of planetary formation and dynamics? And most intriguingly, what does their existence reveal about the universe's capacity for creativity and diversity? The story of exoplanets is a story of wonder, perseverance, and discovery. It is a testament to humanity's unyielding curiosity and our ability to push the boundaries of knowledge. As we embark on this journey, prepare to see the universe and our place in it through an entirely new lens. In the vast expanse of the universe, where countless stars twinkle like distant diamonds, lies one of humanity's greatest revelations: the existence of planets beyond our solar system. Known as exoplanets, these celestial bodies orbit stars other than our Sun, and their discovery has fundamentally changed how we perceive our place in the cosmos. The universe, once imagined as a static and predictable backdrop, has unfolded into a dynamic and diverse arena of worlds, each with its unique story, mysteries, and possibilities. To appreciate the profound significance of exoplanets, one must first journey back to a time when the notion of planets outside our solar system was little more than a speculative dream. For centuries, astronomers peered through rudimentary telescopes, their observations limited to the planets circling our sun. While the idea of other planetary systems wasn't new, philosophers and thinkers had hypothesized their existence. It wasn't until the 20th century that science had the tools and methodology to validate such theories. This marked the beginning of a golden age in astronomy, driven by an insatiable curiosity to answer a simple yet profound question: are we alone? The quest to discover exoplanets was far from straightforward. Unlike stars, which emit light, planets merely reflect it, making them incredibly difficult to detect. Imagine trying to spot a firefly next to a blazing spotlight from miles away. This is the challenge astronomers face when observing planets around distant stars. Yet, through ingenuity and technological advancements, these limitations were overcome, ushering in a new era of discovery. The first confirmed exoplanet detection occurred in 1992 around a pulsar, a type of dead star. This was not only unexpected but also a humbling reminder of how little we truly understood about the universe's diversity. Fast forward to today, and the number of confirmed exoplanets has soared into the thousands, with countless more awaiting verification. Each discovery adds a piece to the cosmic puzzle, revealing systems that range from eerily familiar to wildly alien. Some exoplanets are massive gas giants that dwarf Jupiter, while others are rocky Earth-like worlds that may hold the ingredients for life. Among these discoveries, scientists are not merely cataloging planets, but also seeking answers to some of humanity's oldest questions. How do planets form? Can they sustain life? And if so, what might that life look like? The search for exoplanets is not just a scientific endeavor. It's a profoundly human one. It taps into our innate desire to explore and understand. Exoplanets force us to confront the enormity of the universe and our place within it. They ignite our imagination, inspiring visions of alien landscapes and civilizations. But perhaps most importantly, they remind us that the story of the cosmos is far from complete. For every exoplanet discovered, countless more await, hidden in the shadows, waiting to be unveiled. In this chapter, we will delve deeper into the origins and significance of exoplanetary research. From the earliest hypotheses to the technological breakthroughs that made detection possible, we will explore how these distant worlds have reshaped our understanding of the universe. We will also examine the implications of these discoveries, not just for science, but for humanity's collective imagination. What do exoplanets tell us about the likelihood of life elsewhere? How do they challenge our understanding of planetary formation and dynamics? And most intriguingly, what does their existence reveal about the universe's capacity for creativity and diversity? The story of exoplanets is a story of wonder, perseverance, and discovery. It is a testament to humanity's unyielding curiosity and our ability to push the boundaries of knowledge. As we embark on this journey, prepare to see the universe and our place in it through an entirely new lens. The first exoplanet discovery. History is often marked by moments that transform our understanding of the world and the universe. The discovery of the first exoplanet was one such moment. It wasn't just a milestone in astronomy. It was a revelation that shattered long-held assumptions about the cosmos. This chapter takes you back to the groundbreaking discoveries that confirmed the existence of planets beyond our solar system, tracing the steps that led to this moment and its profound implications for the future of science. For centuries, humanity pondered the question of whether planets existed around other stars. Ancient philosophers speculated about the plurality of worlds, but their ideas were constrained by the lack of evidence. Even as telescopes advanced during the Renaissance, planets outside our solar system remained elusive, too faint and too distant to be detected. The idea persisted, however, in the minds of astronomers and dreamers alike, fueled by a sense of cosmic curiosity. The search for exoplanets gained momentum in the latter half of the 20th century, thanks to advancements in both theory and technology. Scientists began to realize that indirect methods might succeed where direct observation had failed. Among these was the radial velocity method, which detects the gravitational influence of a planet on its host star. A star with an orbiting planet exhibits a subtle wobble as the planet's gravity tugs on it, causing shifts in the star's light spectrum that can be measured from Earth. This method was groundbreaking because it allowed astronomers to infer the presence of planets without needing to see them directly. The first confirmed detection of exoplanets came in 1992, and it happened in one of the unlikeliest of places, a pulsar system. Pulsars are the remnants of massive stars that have exploded in supernovae, leaving behind dense, rapidly spinning neutron stars. These stellar remnants emit beams of radiation, creating a lighthouse effect as they spin. Pulsars are not the kind of stars one would associate with planetary systems. After all, their formation involves a cataclysmic event that should obliterate any surrounding material. Yet, astronomers Alexander Woolsey and Dale Frail discovered two planets orbiting the pulsar PSR B1257+12, located about 2,300 light-years from Earth. These planets, identified through precise measurements of the pulsar's timing, were unlike anything imagined. They were small, rocky worlds in an environment that defied conventional notions of planetary habitability. How could planets survive the explosive death of their host star? The discovery raised more questions than it answered, but confirmed one crucial fact. Planets beyond our solar system were not only possible, they existed. This revelation, while groundbreaking, left some astronomers unsatisfied. Pulsars were rare and peculiar objects, and planets orbiting them were unlikely to be representative of planetary systems around more typical stars. The real breakthrough came 3 years later in 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first exoplanet found orbiting a Sun-like star. 51 Pegasi b was a gas giant about half the mass of Jupiter, located 50 light-years away in the constellation Pegasus. Its orbit was astonishingly close to its star, just 7 million kilometers compared to Earth's 150 million kilometers from the Sun, and it completed a full orbit in a mere 4.2 days. This made it a hot Jupiter, a type of exoplanet that was entirely unexpected at the time. Conventional theories of planetary formation suggested that gas giants should form far from their stars, where temperatures are low enough for gases to condense. Yet 51 Pegasi b was a scorching world, challenging existing models and forcing astronomers to rethink their assumptions. The discovery of 51 Pegasi b was made using the radial velocity method. Mayor and Queloz detected subtle shifts in the star's light spectrum caused by the gravitational pull of the orbiting planet. This method had been theorized for years, but its successful application marked a turning point in exoplanetary science. The finding was met with initial skepticism, as it seemed too unusual to be true. However, follow-up observations confirmed the planet's existence, and it became clear that this was not an isolated case. Similar hot Jupiters began to emerge in the data, suggesting that the universe was far more diverse than previously imagined. The discovery of 51 Pegasi b was celebrated as a triumph of both technology and persistence. It validated decades of theoretical work and demonstrated that detecting exoplanets was not only possible, but practical. This breakthrough set the stage for a new era of discovery, as astronomers raced to apply the radial velocity method to other stars. Within a few years, dozens of exoplanets were identified, each adding to the growing tapestry of planetary diversity. The implications of these early discoveries were profound. They revealed that planetary systems could take forms vastly different from our own, challenging the assumption that our solar system was typical. The realization that planets could exist in extreme environments, close to their stars, orbiting pulsars, or in eccentric orbits, forced scientists to expand their models of planetary formation and dynamics. These findings also fueled speculation about the potential for life beyond Earth. If planets could survive in such diverse conditions, what other surprises might the universe hold? Beyond the scientific implications, the discovery of exoplanets had a profound cultural impact. It captured the imagination of the public, inspiring books, films, and debates about humanity's place in the cosmos. The notion of alien worlds was no longer confined to science fiction. It was a scientific reality. This shift in perspective echoed through fields as diverse as philosophy, art, and theology, as humanity grappled with the realization that we were part of a much larger cosmic story. The discoveries of 1992 and 1995 were just the beginning. They opened the door to a field of research that has grown exponentially in the decades since. Today, the number of confirmed exoplanets exceeds 5,000, with many more awaiting verification. Each new discovery builds on the foundation laid by those first detections, revealing a universe of staggering complexity and wonder. The first exoplanet discoveries taught us that the universe is far stranger and more diverse than we ever imagined. They demonstrated the power of human ingenuity and the importance of questioning assumptions. Perhaps most importantly, they reminded us that the pursuit of knowledge is a journey filled with surprises, challenges, and moments of profound discovery. As we continue to explore the cosmos, these early milestones remain a testament to the unyielding curiosity that drives us to seek answers to the deepest questions of existence. How astronomers detect exoplanets. In the quest to uncover the hidden worlds beyond our solar system, one of the greatest challenges has been simply finding them. Exoplanets, by their very nature, are elusive. They do not emit light like stars, and their faint glow is easily drowned out by the brilliance of their host stars. Detecting them requires extraordinary ingenuity, precision, and a profound understanding of the subtleties of light and motion. Over the past few decades, astronomers have developed ingenious techniques to reveal these distant planets, each method unlocking new possibilities in the search for alien worlds. The story of exoplanet detection begins with the recognition of a fundamental problem. Planets are incredibly small compared to stars. Even the largest gas giants, like Jupiter, are dwarfed by their parent stars, making direct imaging extremely difficult. Compounding this issue is the vast distance separating us from these planets. Imagine trying to spot a tiny marble next to a searchlight from thousands of miles away. That is the scale of the challenge astronomers face. To overcome this, scientists have turned to indirect methods, relying on the effects that planets have on their host stars to infer their existence. The radial velocity method, a star's subtle wobble. One of the earliest and most successful techniques for detecting exoplanets is the radial velocity method, also known as the Doppler wobble method. This approach hinges on the fact that a planet's gravity affects its host star, causing the star to move ever so slightly in response. As the star moves toward and away from Earth, the light it emits shifts in wavelength, a phenomenon known as the Doppler effect. When the star moves toward us, its light becomes slightly bluer. When it moves away, it shifts to redder wavelengths. By meticulously measuring these shifts in a star's spectrum, astronomers can infer the presence of an orbiting planet. They can determine the planet's mass, its orbital period, and even its approximate distance from the star. The radial velocity method was instrumental in the discovery of the first exoplanets, including 51 Pegasi b in 1995. While it works best for detecting massive planets close to their stars, advances in technology have made it possible to detect smaller planets as well. The transit method, shadows in the starlight. While the radial velocity method focuses on a star's motion, the transit method looks for changes in the star's brightness. This technique relies on the fact that when a planet passes or transits in front of its host star from our perspective, it temporarily blocks a small portion of the star's light. The result is a tiny, periodic dip in the star's brightness, which can be measured with extreme precision. The transit method has become one of the most prolific tools for discovering exoplanets, thanks in large part to space-based telescopes like Kepler and TESS, transiting exoplanet survey satellite. These telescopes monitor thousands of stars simultaneously, searching for the telltale dimming caused by transiting planets. By analyzing the duration, depth, and frequency of these dips, astronomers can deduce a planet's size, orbital period, and even its atmospheric composition if the starlight passes through the planet's atmosphere during transit. One of the greatest strengths of the transit method is its ability to detect Earth-sized planets. Kepler alone has identified thousands of exoplanets, many of them in the habitable zone where liquid water could exist. The transit method has also enabled the discovery of multi-planet systems, revealing the intricate dynamics of these distant worlds. Direct imaging, capturing the light of alien worlds. While indirect methods dominate the field, the holy grail of exoplanet detection remains direct imaging, the ability to capture actual pictures of exoplanets. This is an extraordinarily challenging task due to the overwhelming brightness of stars compared to their planets. However, advances in adaptive optics, coronagraphs, and starshade technology have made direct imaging increasingly feasible. Direct imaging works by blocking the star's light while capturing the faint glow of the orbiting planet. This technique has been used to image a handful of exoplanets, particularly young gas giants that emit heat as they cool. While still rare, direct imaging provides invaluable information about a planet's atmosphere, temperature, and even weather patterns. It represents the cutting edge of exoplanet science, offering a glimpse into the future of planetary exploration. Gravitational microlensing, bending light to reveal planets. Another ingenious method for detecting exoplanets is gravitational microlensing, which relies on the warping of space-time by massive objects. According to Einstein's theory of general relativity, a massive object like a star can bend the light of a more distant star behind it, creating a lensing effect. If a planet orbits the foreground star, its gravity can cause a brief, additional magnification of the background star's light. Gravitational microlensing is a powerful tool for detecting planets at great distances from their stars, as well as rogue planets that wander through space unattached to any star. However, it requires precise alignment of stars and is often a one-time event, making it less commonly used than other methods. Astrometry, mapping stellar positions. Astrometry, the oldest method proposed for detecting exoplanets, involves measuring the precise positions and movements of stars over time. A planet's gravitational pull causes its host star to move in a small, circular, or elliptical pattern. By tracking this motion, astronomers can infer the presence of the planet and estimate its mass and orbit. Although astrometry has been challenging to implement due to the extreme precision required, advances in technology have made it a promising method. The European Space Agency's Gaia mission, for example, is conducting astrometric measurements with unprecedented accuracy, which could lead to the discovery of thousands of new exoplanets. Atmospheric studies, decoding alien skies. As detection techniques have advanced, astronomers have begun to focus not just on finding exoplanets, but also on studying their atmospheres. During a planet's transit, some of the starlight passes through its atmosphere, imprinting unique spectral signatures. By analyzing these signatures, scientists can identify the chemical composition of the atmosphere, including the presence of water vapor, carbon dioxide, methane, and other potential indicators of life. The James Webb Space Telescope (JWST) has revolutionized this field, offering unparalleled sensitivity for atmospheric analysis. It has the potential to detect biosignatures, chemical markers that suggest biological activity, on exoplanets in the habitable zone. This capability represents a monumental step in the search for life beyond Earth. The role of AI and machine learning. As the volume of data from exoplanet surveys continues to grow, artificial intelligence, AI, and machine learning have become invaluable tools in the search for exoplanets. Algorithms can sift through vast data sets, identifying patterns and anomalies that might indicate the presence of planets. AI has already helped confirm the existence of several exoplanets and will play an increasingly important role in future discoveries. The future of exoplanet detection. The techniques used to detect exoplanets are constantly evolving, driven by the development of next-generation telescopes and instruments. Projects like the Nancy Grace Roman Space Telescope and ambitious concepts like Starshade's promise to push the boundaries of what we can detect, from smaller planets to faint biosignatures. Meanwhile, ground-based observatories equipped with advanced adaptive optics will complement space missions, providing higher-resolution observations. Each method of exoplanet detection represents a triumph of creativity and determination, overcoming the immense challenges of studying worlds light years away. Together, these techniques have transformed exoplanet science from a speculative endeavor into a thriving field of research, revealing a universe brimming with planets of every kind. As we refine our tools and techniques, the dream of finding another Earth, or even life itself, draws tantalizingly closer. The transit method, peering into shadows. Amid the dazzling array of techniques developed to uncover exoplanets, the transit method stands out as one of the most productive and transformative. Its simplicity belies its power. By observing the dimming of a star's light when a planet crosses in front of it, astronomers can infer a wealth of information about these distant worlds. The transit method has not only revolutionized the search for exoplanets, but also offered unprecedented insights into their properties, unlocking secrets of alien systems that were once beyond our reach. At its core, the transit method relies on the basic principle of light obstruction. When a planet passes between its star and an observer on Earth, it blocks a tiny fraction of the star's light. This causes a temporary dip in brightness, known as a transit, which can be measured with high precision. The size of the dip is directly related to the size of the planet. Larger planets block more light, creating deeper transits, while smaller planets cause subtler dimming. This technique requires patience and persistence. Transits occur only when a planet's orbit aligns perfectly with our line of sight to its star, a cosmic coincidence that happens in a small percentage of systems. Despite this limitation, the transit method has proven extraordinarily effective, thanks in large part to the advent of space-based telescopes like Kepler and TESS, which have monitored thousands of stars simultaneously, searching for these fleeting shadows. The pioneering role of the Kepler Space Telescope. Launched in 2009, the Kepler Space Telescope was a game-changer for exoplanet science. Kepler's mission was simple, yet ambitious: to stare continuously at a single patch of sky, monitoring the brightness of over 150,000 stars for signs of transiting planets. Its ultra-sensitive photometer was capable of detecting brightness changes as small as 0.01%, allowing it to identify Earth-sized planets orbiting Sun-like stars. Kepler's data revealed an astonishing diversity of planetary systems. Among its discoveries were rocky super-Earths, mini-Neptunes, and even planets orbiting multiple stars. Perhaps most importantly, Kepler provided the first statistical evidence that planets are common in the galaxy. It estimated that nearly every star hosts at least one planet, and billions of Earth-sized worlds likely exist in the Milky Way alone. The telescope also uncovered systems that defied expectations. Some stars hosted tightly packed planets in orbital resonances, where their gravitational interactions created harmonious patterns. Others, like the TRAPPIST-1 system, featured multiple Earth-sized planets in the habitable zone, raising the tantalizing possibility of life. Kepler's findings forever changed our understanding of planetary formation and the prevalence of potentially habitable worlds. TESS and the next generation of planet hunting. Building on Kepler's success, the Transiting Exoplanet Survey Satellite, TESS, launched in 2018 with a broader mission: to survey nearly the entire sky. While Kepler focused on a single region, TESS scans multiple sectors, observing millions of stars and prioritizing those closest to Earth. Its goal is to find exoplanets around bright, nearby stars, making them easier to study in detail with ground-based telescopes and future missions like the James Webb Space Telescope. TESS has already identified thousands of exoplanet candidates, including several Earth-sized planets in the habitable zones of their stars. Its wide-field approach has expanded the catalog of known exoplanets and highlighted the immense variety of planetary systems, from compact, multi-planet configurations to gas giants and eccentric orbits. By focusing on nearby stars, TESS is paving the way for detailed characterization of exoplanet atmospheres, compositions, and climates. What we learn from transits. The transit method offers a remarkable depth of information about exoplanets, far beyond their mere existence. By analyzing the light curve, the graph of a star's brightness over time during a transit, astronomers can deduce a planet's size, orbital period, and distance from its star. These parameters, combined with the star's characteristics, reveal critical insights into the planet's nature and environment. For example, the duration and frequency of transits indicate the planet's orbital period and distance from its star. This information allows astronomers to calculate whether the planet lies within the habitable zone, where conditions might allow for liquid water. The depth of the transit reveals the planet's size, enabling scientists to distinguish between rocky worlds, gas giants, and intermediate types like super-Earths and mini-Neptunes. Perhaps the most exciting application of the transit method is the study of exoplanet atmospheres. When a planet transits its star, some of the starlight passes through its atmosphere, imprinting unique spectral signatures. By analyzing these signatures, astronomers can identify the chemical composition of the atmosphere, including the presence of water vapor, carbon dioxide, methane, and other potential biomarkers. This technique, known as transit spectroscopy, has already provided tantalizing glimpses into the atmospheres of distant worlds, hinting at their climates and potential habitability. The challenges and limitations of the transit method. While the transit method is incredibly powerful, it is not without its challenges. One of the most significant limitations is its reliance on precise alignment. Only a small fraction of planetary systems are oriented such that their planets transit from our perspective, meaning the majority of exoplanets remain undetectable by this method. Additionally, transits are periodic events, and capturing multiple transits is necessary to confirm a planet's existence, which can take months or even years for planets with long orbital periods. False positives are another challenge. Stellar activity, eclipsing binary stars, and other phenomena can mimic the signals of transiting planets, requiring careful analysis and follow-up observations to rule out alternative explanations. Despite these obstacles, the transit method remains a cornerstone of exoplanet detection, continually refined by technological advancements and sophisticated data analysis techniques. Beyond detection, the future of transit observations. The transit method is entering a new era, driven by next-generation telescopes and missions that promise unprecedented precision and sensitivity. The James Webb Space Telescope, JWST, launched in 2021, is revolutionizing transit spectroscopy, enabling detailed studies of exoplanet atmospheres with unparalleled clarity. JWST's instruments can detect faint biosignatures, assess the habitability of distant worlds, and explore the chemical diversity of exoplanetary systems. Upcoming missions like the Nancy Grace Roman Space Telescope and ground-based observatories equipped with adaptive optics will complement these efforts, extending the reach of transit studies to smaller, fainter planets and stars. Meanwhile, innovative concepts like star shades, spacecraft designed to block starlight, and enhance direct imaging capabilities promise to expand the scope of exoplanet research even further. A universe revealed through shadows. The transit method has transformed our understanding of the cosmos, revealing a universe teeming with planets of every kind. From blistering hot Jupiters to potentially habitable Earth-sized worlds, transits have unveiled the extraordinary diversity of planetary systems and brought us closer to answering age-old questions about life beyond Earth. Each tiny shadow cast by a transiting planet represents a triumph of human ingenuity, a testament to our ability to extract meaning from the faintest signals in the vastness of space. As technology continues to advance, the transit method will remain at the forefront of exoplanet exploration, guiding us toward new discoveries and deeper insights into the mysteries of the universe. Radial velocity, wobbling stars, and hidden planets. The radial velocity method, often referred to as the Doppler wobble technique, is one of the earliest and most successful tools for detecting exoplanets. Its foundation lies in the subtle gravitational interaction between a star and its orbiting planet, a dance so delicate that only the finest observational techniques can reveal it. This method has played a pivotal role in the discovery of some of the first exoplanets, including the landmark detection of 51 Pegasi b, and continues to be a cornerstone of planetary science. The physics behind the wobble. Every planet exerts a gravitational pull on its host star. While this pull is minuscule compared to the star's own gravitational force, it is sufficient to cause the star to move in a small orbit around the shared center of mass, known as the barycenter. As the star moves, it alternates between approaching and receding from an observer on Earth, causing its light to shift in wavelength due to the Doppler effect. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward the red. By carefully analyzing these shifts in the star's spectral lines, astronomers can detect the periodic motion caused by an orbiting planet. This technique provides critical information about the planet, including its mass, or at least a minimum mass, orbital period, and the shape of its orbit. The breakthrough discovery of 51 Pegasi b. The radial velocity method achieved its first major breakthrough in 1995 with the discovery of 51 Pegasi b, the first confirmed exoplanet orbiting a Sun-like star. Michel Mayor and Didier Queloz observed periodic shifts in the spectral lines of 51 Pegasi, a star located about 50 light-years from Earth. These shifts revealed the presence of a massive planet, roughly half the size of Jupiter, orbiting the star at an astonishingly close distance. This discovery was both groundbreaking and puzzling. 51 Pegasi b, a type of planet now known as a hot Jupiter, challenged existing models of planetary formation. Conventional wisdom suggested that gas giants should form far from their stars, where temperatures are low enough for gases to condense. The existence of a gas giant in such a close, scorching orbit forced scientists to rethink their theories, leading to the development of new models that included planetary migration. How radial velocity works in practice. The radial velocity method involves precise spectroscopic measurements of a star's light. Instruments like high-resolution spectrographs are capable of detecting velocity changes as small as a few meters per second, a level of precision comparable to measuring the speed of a walking human from light-years away. To extract meaningful data, astronomers must account for various factors that can influence a star's spectral lines. Stellar activity, such as flares or spots on the star's surface, can mimic or obscure the signals caused by orbiting planets. Careful calibration, repeated observations, and sophisticated modeling are essential to differentiate genuine planetary signals from noise. Once a periodic Doppler shift is detected, astronomers analyze the amplitude and frequency of the wobble to infer the planet's properties. A larger wobble indicates a more massive planet, while the period of the wobble reveals the time it takes for the planet to complete an orbit. If the planet's orbit is eccentric, the wobble will vary in speed over time, providing further clues about the system's dynamics. Limitations and challenges. While the radial velocity method has been a workhorse for exoplanet detection, it has its limitations. The technique is most sensitive to massive planets orbiting close to their stars, as these exert the strongest gravitational influence and create the largest wobble. Detecting smaller, Earth-sized planets is much more challenging, as their gravitational pull produces only tiny velocity changes. The method also struggles with long-period planets that orbit far from their stars. Such planets cause slow, subtle wobbles that require years or even decades of observation to detect. Additionally, the radial velocity method provides only a minimum estimate of a planet's mass, as it cannot determine the inclination of the planet's orbit relative to our line of sight. This uncertainty means that the true mass of the planet could be significantly higher than the observed minimum. Despite these challenges, advances in technology have steadily improved the sensitivity of radial velocity measurements. Modern spectrographs, such as HARP's High-Accuracy Radial Velocity Planet Searcher and ESPRESSO, are capable of detecting velocity changes as small as 10 centimeters per second, enabling the detection of smaller and more distant planets. The role of radial velocity in multi-planet systems. The radial velocity method has proven invaluable for studying systems with multiple planets. By analyzing the overlapping signals from multiple wobbles, astronomers can identify the presence of several planets and characterize their masses and orbits. This has led to the discovery of complex systems, such as the Gliese 581 system, which features multiple planets, including potential candidates for habitability. The method has also revealed fascinating interactions between planets in multi-planet systems. For example, the gravitational pull of one planet can influence the orbit of another, creating measurable variations in their radial velocity signals. These interactions provide insights into the dynamics and stability of planetary systems, as well as clues about their formation and evolution. Combining radial velocity with other methods. Radial velocity often works in tandem with other detection techniques, particularly the transit method. When a planet is detected through both radial velocity and transits, astronomers can determine its density and composition. For instance, a planet with a low density is likely a gas giant, while a high-density planet may be rocky and Earth-like. This combination has been instrumental in characterizing a wide range of exoplanets, from super-Earths to mini-Neptunes. The synergy between radial velocity and direct imaging is also promising. While radial velocity reveals a planet's mass and orbit, direct imaging can provide information about its atmosphere, temperature, and even surface features. Together, These methods offer a comprehensive view of exoplanetary systems. The future of radial velocity. As technology advances, the radial velocity method continues to push the boundaries of what we can detect. Next-generation spectrographs and telescopes are poised to achieve even greater precision, enabling the detection of Earth-like planets in the habitable zones of their stars. Projects like the European Southern Observatory's extremely large telescope, YELT, and the 30-meter telescope, TMT, will play a pivotal role in this effort, providing the sensitivity needed to detect tiny velocity shifts caused by small, distant planets. In addition to detecting new planets, radial velocity is shedding light on the early stages of planetary formation. By studying the wobbles of young stars, astronomers can infer the presence of protoplanets, planets still in the process of forming, offering a glimpse into the dynamic processes that shape planetary systems, a method that changed everything. The radial velocity method has been instrumental in transforming exoplanet science from a speculative field into a thriving area of research. It was the technique that first revealed the existence of exoplanets around sun-like stars, and it continues to uncover new worlds with remarkable precision. Its success lies not only in its technical sophistication, but also in the ingenuity and perseverance of the scientists who developed and refined it. Every wobble detected, no matter how faint, is a testament to the interconnectedness of the universe, a reminder that even the smallest gravitational forces can leave measurable imprints across the cosmos. As we continue to refine this technique, the radial velocity method will remain a vital tool in our quest to understand the nature of planets and their place in the grand tapestry of the universe. The role of space telescopes in exoplanet discovery. In the grand quest to uncover worlds beyond our solar system, space telescopes have emerged as indispensable tools, revolutionizing the field of exoplanet science. Freed from the distortions of Earth's atmosphere, these orbiting observatories have provided astronomers with a crystal-clear view of the cosmos, enabling discoveries that were once unimaginable. From detecting faint planetary signals to analyzing distant atmospheres, space telescopes have transformed our understanding of the universe and expanded the boundaries of what we consider possible. Why space telescopes are essential. Earth's atmosphere, while vital for life, poses significant challenges for astronomers. Turbulence causes stars to twinkle, scattering their light and blurring observations. Additionally, the atmosphere absorbs and distorts certain wavelengths of light, particularly in the ultraviolet and infrared ranges, which are crucial for studying exoplanets. Ground-based telescopes, no matter how advanced, are limited by these constraints. Space telescopes operate above the atmosphere, offering a pristine vantage point. They can detect subtle changes in starlight caused by orbiting planets and capture data across a broad range of wavelengths. This capability is especially important for studying the faint signals of small, distant exoplanets and for analyzing their atmospheres for potential signs of life. The Kepler Space Telescope, a pioneer in planet hunting. Launched in 2009, the Kepler Space Telescope was the first mission specifically designed to search for exoplanets. Its innovative approach involved monitoring the brightness of over 150,000 stars in a fixed patch of sky, looking for the tiny dips in light caused by transiting planets. Kepler's sensitivity allowed it to detect changes in brightness as small as 0.01%, enabling the discovery of Earth-sized planets orbiting distant stars. Kepler's contributions to exoplanet science are nothing short of revolutionary. It identified thousands of exoplanets, ranging from massive gas giants to rocky worlds similar in size to Earth. Among its most significant findings was the realization that planets are ubiquitous in the galaxy. Nearly every star, Kepler revealed, is likely to host at least one planet, and many have entire systems of planets orbiting them. The telescope also provided invaluable data on planetary diversity. It uncovered a range of exotic worlds, including super-Earths, mini-Neptunes, and planets in multi-star systems. Perhaps most tantalizingly, Kepler identified several planets in the habitable zone, where conditions might allow for liquid water, a key ingredient for life. Despite a mechanical failure in 2013 that ended its primary mission, Kepler continued its work under the K2 mission, using a modified technique to survey new regions of the sky. Its legacy endures as one of the most successful and impactful space telescopes in history. TESS, expanding the search closer to home. Building on Kepler's success, the Transiting Exoplanet Survey Satellite, TESS, launched in 2018 with a complementary mission. While Kepler focused on a distant, narrow field of view, TESS was designed to survey nearly the entire sky, prioritizing nearby stars. Its primary goal is to identify exoplanets around bright, nearby stars, making them easier to study with ground-based telescopes in future missions. TESS's wide-field approach has already yielded thousands of exoplanet candidates, including small, rocky worlds in the habitable zones of their stars. By focusing on nearby systems, TESS has opened the door to detailed characterization of these planets, paving the way for studies of their atmospheres, compositions, and potential habitability. The James Webb Space Telescope, a new era of exoplanet science. The James Webb Space Telescope, JWST, launched in 2021, represents a monumental leap forward in exoplanet research. With its large, segmented mirror and advanced instruments, JWST is designed to operate in the infrared spectrum, allowing it to study the faint heat signatures of distant planets. Its unprecedented sensitivity makes it possible to analyze the atmospheres of small, rocky exoplanets, an essential step in the search for life. JWST's capabilities include transit spectroscopy, which examines the light that passes through a planet's atmosphere during a transit. This technique can identify the chemical composition of the atmosphere, including the presence of water vapor, carbon dioxide, methane, and other potential biosignatures. By studying planets in the habitable zones of their stars, JWST has the potential to detect the chemical fingerprints of life itself. Beyond individual planets, JWST is also exploring the broader dynamics of planetary systems, investigating how planets form, migrate, and interact with their stars. Its findings are expected to transform our understanding of exoplanetary science, providing new insights into the origins of our own solar system. Hubble and Spitzer, pioneers of exoplanet atmosphere studies. While not originally designed for exoplanet research, the Hubble Space Telescope and the now-retired Spitzer Space Telescope have made significant contributions to the field, particularly in the study of exoplanet atmospheres. Hubble's ability to observe ultraviolet and visible light has been instrumental in identifying atmospheric components, such as water vapor and haze, on distant planets. Spitzer, with its infrared capabilities, excelled at detecting the heat signatures of exoplanets, providing insights into their temperatures and weather patterns. It was also a pioneer in studying the atmospheres of smaller, rocky planets, laying the groundwork for future missions like JWST. Together, these telescopes demonstrated the power of multi-wavelength observations in revealing the properties of distant worlds. The future of space telescopes. As remarkable as current space telescopes are, the future promises even greater advances. Several ambitious missions are on the horizon, each designed to address specific challenges in exoplanet science. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will use a wide-field approach to survey large areas of the sky, complementing TESS and JWST. Its coronagraph will enable direct imaging of exoplanets, allowing astronomers to study their atmospheres and climates. Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, a European mission set to launch in 2029, will focus exclusively on characterizing exoplanet atmospheres, providing a detailed census of their chemical compositions and thermal properties. Concepts like LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, represent the next generation of space telescopes, designed to detect and study Earth-like planets in unprecedented detail. These missions aim to directly image exoplanets in the habitable zones of their stars and search for biosignatures, bringing us closer to answering the question of whether we are alone in the universe. Space telescopes and the search for life. The ultimate goal of exoplanet research is to find signs of life beyond Earth. Space telescopes are at the forefront of this effort, providing the tools to detect and analyze the conditions necessary for habitability. By studying the atmospheres of rocky planets in the habitable zones of their stars, telescopes like JWST and future missions may identify the chemical markers of biological activity, such as oxygen, methane, or ozone. The implications of such a discovery would be profound, reshaping our understanding of life's place in the universe and sparking new questions about its origins, diversity, and potential for interstellar communication. A cosmic perspective. Space telescopes have fundamentally changed the way we see the universe. They have revealed a galaxy teeming with planets, each a potential harbor for life, or a unique window into the processes that shape planetary systems. Through their lenses, we have glimpsed the astonishing variety of worlds that exist beyond our own, from scorching hot Jupiters to icy rogue planets drifting through the void. As technology continues to advance, space telescopes will remain at the forefront of exoplanet discovery, pushing the boundaries of what we can observe and understand. They are not just instruments of science, but also symbols of human curiosity and ingenuity. A reminder that, no matter how vast the cosmos may seem, we are always reaching for the stars. Types of exoplanets. A universe of diversity. The discovery of exoplanets has unveiled a cosmos brimming with diversity, revealing worlds that defy our expectations and stretch the boundaries of what we thought possible. These planets, orbiting stars across the galaxy, come in an astonishing variety of sizes, compositions, and orbital configurations. Some resemble the familiar planets of our solar system, while others are utterly alien, challenging existing theories of planetary formation and dynamics. This chapter explores the rich taxonomy of exoplanets, from gas giants to rocky Earth-like worlds, and highlights the scientific significance of their extraordinary variety. Gas giants, the titans of the cosmos. Among the most striking exoplanets are gas giants, massive planets composed primarily of hydrogen and helium. These worlds are similar in composition to Jupiter and Saturn, though their properties can vary widely. Gas giants are among the easiest exoplanets to detect due to their size and strong gravitational influence on their host stars, making them some of the first exoplanets to be discovered. One fascinating subset of gas giants is hot Jupiters, planets with masses comparable to or greater than Jupiter, but orbiting extremely close to their stars. These planets often complete an orbit in just a few days, exposing them to intense heat and radiation. This proximity gives rise to extreme atmospheric conditions, including temperatures hot enough to vaporize metals and winds that reach thousands of kilometers per hour. Some hot Jupiters, such as HD 209458b, even exhibit phenomena like atmospheric escape, where particles are stripped away by stellar radiation. Other gas giants, like cold Jupiters, orbit farther from their stars, resembling the gas giants in our solar system. These planets are typically cooler and may host extensive moon systems. The study of such planets provides insights into the formation and evolution of gas giants and their potential to influence the architecture of planetary systems. Super-Earths and mini-Neptunes, the missing middle. One of the most intriguing findings of exoplanet science is the prevalence of super-Earths and mini-Neptunes, planet types not found in our solar system. Super-Earths are rocky planets larger than Earth, but smaller than Neptune, often with masses up to 10 times that of our planet. These worlds occupy a fascinating middle ground, with conditions that could range from Earth-like to entirely alien. Mini-Neptunes, on the other hand, are smaller versions of Neptune, with thick atmospheres of hydrogen and helium surrounding rocky or icy cores. These planets blur the line between terrestrial and gas-dominated worlds, raising questions about their formation and structure. Are mini-Neptunes failed gas giants, or do they represent an entirely different evolutionary pathway? The prevalence of super-Earths and mini-Neptunes suggests that they may be among the most common types of planets in the galaxy. Their potential to support life depends on their atmospheres, surface conditions, and proximity to their stars. Some super-Earths, like Kepler 452b, have been identified in the habitable zones of their stars, making them prime candidates for further study. Earth-like worlds, the search for another home. The discovery of Earth-like exoplanets, rocky planets similar in size and composition to Earth, has captivated scientists and the public alike. These worlds are of particular interest because they may possess conditions suitable for life. The key factor in determining their habitability is their location within the habitable zone, the region around a star where temperatures allow for liquid water to exist. Among the most promising candidates are planets like Proxima Centauri b, located in the habitable zone of the star closest to our Sun, and the planets in the TRAPPIST-1 system, a group of 7 Earth-sized worlds orbiting a red dwarf star. 3 of these planets lie in the habitable zone, raising the tantalizing possibility of life. The discovery of such systems highlights the potential for Earth-like planets to exist in a variety of stellar environments, from Sun-like stars to cooler, dimmer red dwarfs. Ice giants, frozen behemoths. Ice giants, like Uranus and Neptune in our solar system, are composed of heavier elements, such as water, ammonia, and methane, rather than hydrogen and helium. While these planets are relatively rare among the exoplanets discovered so far, this may be due to observational biases rather than actual scarcity. Ice giants are thought to form in the colder, outer regions of planetary systems, where icy materials can condense. Their unique compositions make them valuable targets for studying the chemistry of planetary formation and the potential for exotic atmospheric phenomena, such as high-altitude clouds of methane or ammonia. Water worlds, oceans without end. The concept of water worlds, planets completely covered by vast global oceans, has long captured the imagination of scientists and science fiction writers. These planets may have deep oceans hundreds or even thousands of kilometers thick, covering rocky or icy cores. Such environments could provide the conditions necessary for life, particularly in subsurface oceans protected from harsh stellar radiation. Water worlds are thought to form in regions of planetary systems rich in water ice, which melts as the planet migrates closer to its star. The study of these planets is critical for understanding the range of conditions under which life might arise. Some exoplanets, like GJ1214b, have been identified as potential water worlds, with atmospheres rich in water vapor. Rogue planets, wanderers of the void. Not all planets are bound to stars. Rogue planets, also known as free-floating planets, drift through interstellar space without a host star. These enigmatic worlds are thought to form in planetary systems, but are ejected due to gravitational interactions or collisions. Alternatively, they may form directly from collapsing clouds of gas and dust, like stars. Despite their isolation, rogue planets may retain heat generated by internal processes or radioactive decay, allowing subsurface oceans to exist beneath icy crusts. Detecting rogue planets is challenging, but techniques like gravitational microlensing have identified several candidates, including some with masses comparable to Earth. Exoplanets in binary and multi-star systems. Some of the most fascinating planetary systems are those that orbit multiple stars. Planets in binary systems orbits can experience complex gravitational interactions, leading to unusual orbital dynamics. For instance, planets in circumbinary orbits circle both stars, much like the fictional world of Tatooine from Star Wars. Such systems provide a natural laboratory for studying planetary stability and formation. Despite the challenges of their environments, planets in binary systems are not uncommon, suggesting that planet formation is remarkably resilient even in dynamic stellar systems. The strangest exoplanets, outliers of the universe. Exoplanet discoveries have included some truly bizarre worlds that challenge our understanding of what a planet can be. For example, Kepler-10c, nicknamed the Mega-Earth, is a rocky planet 17 times the mass of Earth, defying models of planetary formation. WASP-12b, a hot Jupiter, is so close to its star that it is being pulled apart by tidal forces, forming a comet-like tail. PSRB 1620-26b, often called the Methuselah planet, orbits a binary system of a pulsar and a white dwarf, making it one of the oldest known planets in the universe. These outliers expand our understanding of planetary diversity and force us to continually revise our theories. A universe of infinite possibilities. The diversity of exoplanets reflects the incredible creativity of the cosmos. Each discovery adds a piece to the puzzle, revealing new insights into how planets form, evolve, and interact with their environments. From fiery hot Jupiters to icy rogue planets, the variety of worlds in the galaxy suggests that nature's imagination knows no bounds. As we continue to explore, the ultimate goal remains clear: to find a world that mirrors our own, or perhaps one that surprises us with entirely new possibilities. The universe, it seems, is a tapestry woven with infinite threads, each representing a unique planetary story waiting to be told. Hot Jupiters, giant worlds in strange orbits. Among the most intriguing and perplexing discoveries in exoplanet science are hot Jupiters, gas giants that defy conventional planetary formation theories. These colossal planets, similar in size and composition to Jupiter, orbit extraordinarily close to their host stars, often completing an orbit in just a few days. Their proximity subjects them to extreme temperatures and radiation, creating environments that challenge our understanding of planetary dynamics and evolution. This chapter delves into the phenomenon of hot Jupiters, exploring their unique characteristics, formation theories, and the mysteries they continue to pose. The discovery that changed everything. The first confirmed hot Jupiter, 51 Pegasi b, was discovered in 1995 by Michel Mayor and Didier Queloz using the radial velocity method. This gas giant stunned the astronomical community. It was about half the mass of Jupiter, but orbited its star at a distance of just 7 million kilometers, approximately 20 times closer than Mercury is to the Sun. Its orbital period was a mere 4.2 days, earning it the distinction of being the first planet discovered around a Sun-like star. At the time, this discovery seemed almost impossible. Existing models of planetary formation, based on our own solar system, suggested that gas giants should form far from their stars, beyond the frost line, where temperatures are low enough for volatile compounds like water to condense into solid ice. The existence of a gas giant so close to its star upended these theories and forced astronomers to rethink how planets form and migrate. Characteristics of hot Jupiters. Hot Jupiters share several defining characteristics that make them distinct from other types of exoplanets. 1. Size and composition. Like Jupiter, hot Jupiters are composed primarily of hydrogen and helium, with thick atmospheres and relatively low densities. Some hot Jupiters are even larger than Jupiter due to the intense heat from their stars, which causes their atmospheres to expand. 2. Close proximity to host stars. These planets orbit extremely close to their stars, typically within 0.1 astronomical units, AU, much closer than Mercury's 39 cents from the Sun. This proximity subjects them to extreme stellar radiation and tidal forces. 3. Short orbital periods. Hot Jupiters often have orbital periods of just a few days, making their detection relatively straightforward using methods like radial velocity and transits. 4. High temperatures. Surface temperatures on hot Jupiters can exceed 2000 Kelvin, over 3000 degrees Fahrenheit, leading to exotic atmospheric conditions, including the vaporization of metals and the formation of unusual clouds and weather patterns. Formation and migration. Theories and challenges. The existence of hot Jupiters poses a fundamental question. How do such massive planets end up so close to their stars? Astronomers have developed several theories to explain their origins. 1. Planetary migration. The leading hypothesis is that hot Jupiters form beyond the frost line, where gas and ice are abundant, and then migrate inward due to interactions with the protoplanetary disk. As the young planet interacts with the disk's gas and dust, it loses angular momentum and spirals closer to its star. This migration must occur early in the planet's life, as the disk dissipates within a few million years. 2. Gravitational interactions. In multi-planet systems, gravitational interactions can destabilize orbits, causing a planet to be flung inward toward its star. This process, known as planet-planet scattering, can result in the creation of hot Jupiters. Once the planet settles into a close orbit, tidal forces circularize its path. 3. In situ formation. An alternative theory suggests that hot Jupiters form close to their stars, defying the traditional frost line model. In this scenario, local concentrations of gas and dust in the inner regions of the protoplanetary disk could enable the rapid formation of a gas giant. However, this theory is less favored due to the challenges of accreting sufficient material so close to the star. Extreme environments and exotic atmospheres. The proximity of hot Jupiters to their stars creates some of the most extreme environments in the universe. Their intense heat and radiation lead to atmospheric conditions that are both fascinating and hostile. 1. Atmospheric expansion and escape. The high temperatures cause the atmospheres of hot Jupiters to expand, sometimes to the point where they are being stripped away by stellar radiation. This phenomenon, known as atmospheric escape, has been observed on planets like HD 209458b, where hydrogen gas forms a massive tail trailing behind the planet. 2. Clouds and weather patterns. Hot Jupiters exhibit dynamic and exotic weather systems. Observations have revealed clouds composed of materials like titanium oxide, silicates, and even vaporized metals. Winds on these planets can reach thousands of kilometers per hour, redistributing heat from the day side to the night side. 3. Thermal inversions. Some hot Jupiters exhibit thermal inversions, where temperatures increase with altitude rather than decrease. These inversions are thought to be caused by high-altitude compounds that absorb stellar radiation, creating a hot stratosphere. 4. Rain of liquid gems. Theoretical models suggest that some hot Jupiters may experience rain composed of molten materials like iron, or even liquid rubies and sapphires, formed from condensed aluminum oxides in their atmospheres. Observational insights. What hot Jupiters teach us. Despite their extreme nature, hot Jupiters have provided invaluable insights into planetary science. They are among the easiest exoplanets to detect due to their size and close orbits, making them ideal for detailed study. Their atmospheres, for example, are more readily observed during transits, when starlight passes through the planet's atmosphere and creates spectral signatures. By studying hot Jupiters, astronomers have gained a better understanding of 1. Planetary formation and migration. The discovery of hot Jupiters has fundamentally reshaped theories of planetary formation, emphasizing the importance of migration and dynamical interactions in shaping planetary systems. 2. Atmospheric physics. Observations of hot Jupiters have advanced the study of exoplanet atmospheres, revealing the effects of extreme heat and radiation on atmospheric composition and dynamics. 3. Stellar planet interactions. The close proximity of hot Jupiters to their stars provides a natural laboratory for studying tidal interactions, stellar activity, and their effects on planetary evolution. Outliers among hot Jupiters. Not all hot Jupiters conform to the same patterns. Some, like WASP 12b, are so close to their stars that they are being tidally distorted, creating egg-shaped profiles. Others, like HD 80606b, have highly eccentric orbits, experiencing extreme temperature swings as they approach and retreat from their stars. One of the most intriguing outliers is KLT 9b, the hottest known exoplanet, with surface temperatures exceeding 4,000 Kelvin, 7,000 degrees Fahrenheit. This planet's intense heat makes its atmosphere resemble that of a star more than a planet. The legacy and future of hot Jupiter research. Hot Jupiters have been instrumental in shaping the field of exoplanet science. They were the first exoplanets discovered, and their study has driven advancements in detection techniques, atmospheric characterization, and theoretical modeling. While they may not be hospitable to life, their extreme environments provide a unique opportunity to explore the outer limits of planetary science. Future missions, such as the James Webb Space Telescope, JWST, and upcoming ground-based observatories, promise to reveal even more about these fascinating worlds. By studying their atmospheres, compositions, and interactions with their stars, astronomers will continue to unlock the secrets of hot Jupiters and their role in the cosmic ballet of planetary systems. Super-Earths and mini-Neptunes, a cosmic middle ground. In the vast and varied catalog of exoplanets, two types stand out for their intriguing characteristics and prevalence: super-Earths and mini-Neptunes. These planets represent a middle ground between small rocky worlds like Earth and massive gas giants like Neptune, offering a glimpse into a category of planets absent in our solar system. They dominate the landscape of discovered exoplanets, suggesting they may be the most common planet types in the galaxy. This chapter explores the unique features, formation theories, and potential habitability of these enigmatic worlds. What are super-Earths? Super-Earths are planets larger than Earth, but smaller than Neptune, typically with masses ranging from 1.5 to 10 Earth masses. Despite their name, super-Earths refer only to a planet's size and mass, not its composition or habitability. These planets may be rocky like Earth, composed of thick layers of ice, or even feature substantial gaseous envelopes. Super-Earths can vary significantly in density and structure. Rocky super-Earths, planets with dense, solid compositions similar to Earth's, potentially harboring liquid water and atmospheres conducive to life. Icy super-Earths, worlds with thick layers of water ice or frozen gases, typically forming farther from their stars. Gas-enveloped super-Earths, planets with a rocky or icy core surrounded by a thin hydrogen-helium atmosphere. What are mini-Neptunes? Mini-Neptunes are slightly larger than super-Earths, with masses and radii that place them between Earth and Neptune. These planets often have thick hydrogen and helium atmospheres, which give them lower densities than rocky planets. Mini-Neptunes are thought to form in regions rich in gas, where they accumulate substantial atmospheres but not enough to become full-fledged gas giants. These planets have the following features. Substantial atmospheres. Their thick atmospheres create unique thermal and chemical environments. Intermediate density. Mini-Neptunes are less dense than rocky planets but denser than gas giants, pointing to a hybrid composition of cores and gaseous layers. Why are they so common? Super-Earths and mini-Neptunes are among the most frequently discovered types of exoplanets, a finding largely attributed to the sensitivity of current detection methods. Space telescopes like Kepler and TESS have revealed that planets with sizes between Earth and Neptune are abundant in the galaxy, far outnumbering gas giants or terrestrial planets. One hypothesis for their ubiquity is that their size and composition make them easier to form. In protoplanetary disks, smaller planets can form rapidly and avoid the runaway gas accretion that produces gas giants. This efficiency in formation makes them natural outcomes of planetary evolution in many systems. Formation and evolution. Theories about the formation and evolution of super-Earths and mini-Neptunes suggest diverse pathways. 1. In situ formation. These planets may form close to their stars, accreting material from dense regions of the protoplanetary disk. The proximity to the star limits the amount of gas they can gather, resulting in smaller atmospheres. 2. Core accretion and migration. Some super-Earths and mini-Neptunes form farther from their stars, beyond the frost line, where icy materials are abundant. After forming a substantial core, these planets migrate inward due to gravitational interactions with the disk or other planets, stopping before they accumulate enough gas to become giants. 3. Atmospheric loss. Some mini-Neptunes may evolve into super-Earths through atmospheric loss. Stellar radiation and wind can strip away their thick gaseous envelopes over time, leaving behind denser, rocky cores. Habitability of super-Earths. The potential for habitability makes super-Earths particularly exciting targets for study. Their larger mass and size can produce higher surface gravity, which in turn affects their ability to retain atmospheres. A thicker atmosphere can provide better protection against cosmic radiation and create stable climates. Key factors influencing habitability include location in the habitable zone. Planets within the habitable zone of their stars may maintain liquid water, a critical ingredient for life. Atmospheric composition. A balance of greenhouse gases, such as carbon dioxide and water vapor, could create temperatures suitable for life. Geological activity. Larger planets may have active tectonics and volcanism, which can regulate carbon cycles and maintain atmospheric stability. Some notable super-Earth candidates for habitability include Kepler 452b, often called Earth's cousin. This planet lies in the habitable zone of a sun-like star and has conditions that may allow for liquid water. LHS 1140b, a rocky super-Earth in the habitable zone with a dense atmosphere and potential for liquid water. The unique challenges of mini-Neptunes. While mini-Neptunes are less likely to be habitable due to their thick atmospheres, they offer intriguing environments for study. Their substantial gas envelopes create extreme pressures and temperatures, making them more similar to ice giants like Neptune than to terrestrial planets. However, the potential for habitable moons orbiting mini-Neptunes adds a new layer of complexity to their study. Atmospheric studies. Unveiling alien skies. Recent advancements in transit spectroscopy have enabled detailed studies of the atmospheres of super-Earths and mini-Neptunes. Space telescopes like the James Webb Space Telescope, JWST, are expected to provide critical insights into these planets' atmospheres, including the detection of water vapor, methane, and other molecules. Some breakthroughs in atmospheric studies include GJ-1214b, one of the best-studied mini-Neptunes. Its atmosphere has revealed signs of water vapor and thick clouds. K2-18b, a super-Earth/mini-Neptune hybrid with detected water vapor, making it a candidate for further exploration. The dichotomy of super-Earths and mini-Neptunes. One of the most intriguing aspects of these planets is the apparent dichotomy between rocky super-Earths and gaseous mini-Neptunes. Studies suggest a radius gap at around 1.6 Earth radii, where planets transition from rocky to gas-enveloped. This gap reflects the impact of stellar radiation and atmospheric loss on planet evolution, offering a window into the processes that shape planetary diversity. What these planets tell us about the galaxy. Super-Earths and mini-Neptunes have revolutionized our understanding of planet formation and evolution. Their abundance challenges the notion that our solar system represents a typical planetary system. Instead, these planets suggest that nature favors a wider variety of outcomes, with configurations and environments vastly different from our own. They also underscore the importance of studying intermediate-sized planets, which may hold the key to understanding the continuum between terrestrial worlds and gas giants. By probing their atmospheres, compositions, and orbits, astronomers can refine models of planetary evolution and uncover the factors that govern habitability. A new frontier in exploration. The discovery of super-Earths and mini-Neptunes marks a new frontier in the exploration of alien worlds. As space telescopes and observational techniques continue to improve, these planets will remain prime targets for research, offering tantalizing glimpses into the diversity of the cosmos. Whether as potential harbors for life or as natural laboratories for studying planetary physics, they hold the promise of answering some of the most profound questions about our place in the universe. Rogue planets, wanderers of the cosmos. In the vast and seemingly infinite expanse of the universe, where stars illuminate the darkness and planets orbit in well-defined paths, there exists a class of worlds that defy these norms. Rogue planets. These enigmatic wanderers drift alone through interstellar space, untethered to any star. Their existence challenges traditional ideas of planetary formation and raises fascinating questions about the nature of planets and their potential for life in the most unexpected places. This chapter delves into the mysteries of rogue planets, exploring their origins, characteristics, and the tantalizing possibility that they may harbor subsurface life. What are rogue planets? Rogue planets, also known as free-floating planets or nomadic planets, are celestial bodies that do not orbit a star. Instead, they travel through the galaxy on solitary trajectories, their paths influenced only by the gravitational forces of the Milky Way. These planets lack the radiant warmth of a host star, existing in perpetual cold and darkness. Despite their isolation, rogue planets share many characteristics with conventional planets. They can range in size from Earth-like to gas giant proportions, and their compositions may include rock, ice, gas, or a combination thereof. What sets them apart is their independence. While most planets form and remain within the gravitational pull of a star, rogue planets have been ejected from their systems or formed in isolation. How do rogue planets form? The existence of rogue planets poses intriguing questions about their formation. Astronomers have proposed two primary mechanisms by which these solitary worlds come into being. 1. Ejection from planetary systems. Rogue planets are often thought to originate within traditional planetary systems. During the chaotic early stages of planetary formation, gravitational interactions between forming planets, protoplanetary disks, and nearby stars can destabilize orbits. In some cases, these interactions result in a planet being flung out of its system, leaving it to wander the galaxy. This process, known as dynamical ejection, is particularly common in dense star-forming regions where gravitational encounters are frequent. 2. Formation and isolation. An alternative theory suggests that rogue planets may form directly from collapsing clouds of gas and dust, much like stars. If a cloud is too small to ignite nuclear fusion, it may still condense into a planetary mass object. These free-floating planets resemble failed stars and may include gas giants or icy worlds. The challenges of detecting rogue planets. Detecting rogue planets is one of the greatest challenges in modern astronomy. Without a host star to illuminate them, these planets emit little to no visible light, rendering them effectively invisible to conventional telescopes. However, astronomers have developed ingenious techniques to identify these elusive objects. 1. Gravitational microlensing. The most successful method for detecting rogue planets is gravitational microlensing, which leverages the warping of space-time by massive objects. When a rogue planet passes in front of a distant star, its gravity acts as a lens, magnifying the star's light. This brief, transient event can reveal the presence of the planet, along with its mass and distance. Microlensing has been instrumental in identifying several rogue planet candidates, including those with masses comparable to Earth and Jupiter. 2. Infrared observations. Rogue planets, particularly young ones, may retain residual heat from their formation, emitting faint infrared radiation. Space-based telescopes like the James Webb Space Telescope (JWST) and the Wide Field Infrared Survey Telescope (WFRST) are well suited for detecting this thermal emission, providing valuable data about the planet's sizes and compositions. The characteristics of rogue planets. The rogue planets discovered so far exhibit a wide range of properties, reflecting the diversity of planetary formation processes. 1. Gas giant rogue planets. Many rogue planets identified to date are gas giants, similar in size and composition to Jupiter. These planets are thought to form in the outer regions of planetary systems, where gravitational interactions are most likely to eject them into interstellar space. 2. Earth-sized rogue planets. Smaller rogue planets, with masses and sizes comparable to Earth, are more difficult to detect, but are likely to be far more numerous. These rocky wanderers may have solid surfaces, ice layers, or even subsurface oceans, depending on their compositions and thermal histories. 3. Icy rogue planets. Rogue planets located in colder regions of the galaxy may be composed primarily of ice, with surfaces covered in frozen water, methane, or ammonia. These icy worlds may retain internal heat, raising intriguing possibilities for subsurface liquid environments. Can rogue planets support life? The absence of a host star does not necessarily preclude the possibility of life on rogue planets. While their surfaces are likely frigid and barren, their interiors may tell a different story. Several factors could make rogue planets hospitable, at least for microbial life. 1. Internal heat sources. Many planets generate heat through radioactive decay and residual energy from their formation. This internal heat could sustain subsurface oceans beneath layers of ice, creating environments similar to those found on icy moons like Europa and Enceladus in our solar system. 2. Thick atmospheres. A dense atmosphere rich in greenhouse gases could trap internal heat, preventing the planet's surface from freezing entirely. Such an atmosphere might also support chemical reactions necessary for life. 3. Tidal heating. Rogue planets with moons or binary companions could experience tidal heating, a process in which gravitational interactions generate heat through friction. This mechanism has been observed in moons like Io, which remains geologically active despite its distance from the Sun. The discovery of even microbial life on a rogue planet would revolutionize our understanding of habitability, demonstrating that life can thrive in environments far removed from the warmth of a star. The role of rogue planets in galactic evolution. Rogue planets may play a more significant role in the galaxy than previously thought. They could serve as reservoirs of material, potentially seeding star-forming regions with elements and compounds. Additionally, their abundance provides clues about the dynamics of planetary systems and the processes that shape their evolution. Future missions and the search for rogue planets. Upcoming missions and technological advancements promise to shed new light on rogue planets. The Nancy Grace Roman Space Telescope and ground-based observatories like the Extremely Large Telescope, ELT, will enhance our ability to detect and study these elusive worlds. Future gravitational microlensing surveys, combined with infrared imaging, may reveal thousands of rogue planets, offering a more comprehensive picture of their population and diversity. A cosmic mystery. Rogue planets represent one of the most mysterious and captivating phenomena in the universe. They challenge our understanding of planetary formation and raise profound questions about the potential for life in the coldest, darkest corners of space. As we continue to explore the cosmos, these solitary wanderers remind us that the universe is full of surprises, waiting to be discovered. The habitable zone, where life could thrive. In the search for life beyond Earth, one concept has become central to our understanding of planetary habitability: the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where conditions might allow liquid water to exist on a planet's surface, neither too hot nor too cold. Water, being essential for all known life, serves as the foundation for defining this zone. The study of the habitable zone not only guides the search for potentially life-supporting exoplanets, but also deepens our understanding of what makes a planet capable of sustaining life. What is the habitable zone? The habitable zone is defined as the orbital region around a star where temperatures allow for liquid water to exist. The exact boundaries of this zone depend on the luminosity and type of the star, as well as the planet's atmospheric composition and other factors that influence its surface temperature. For example, inner boundary. Too close to the star, a planet's surface becomes too hot, causing water to evaporate and potentially triggering a runaway greenhouse effect, as seen on Venus. Outer boundary. Too far from the star, a planet's surface freezes, turning water into ice and making liquid water unlikely, as observed on Mars today. In our solar system, the habitable zone spans from just beyond Venus's orbit to slightly beyond Mars's orbit, with Earth sitting comfortably within this range. However, even within the habitable zone, other factors such as atmospheric pressure, greenhouse gas composition, and geological activity play critical roles in determining whether a planet can actually support life. Habitable zones around different types of stars. The habitable zone varies significantly depending on the type of star. Stars differ in size, temperature, and lifespan, which affect the extent and location of their habitable zones. 1. Sun-like stars, G-type stars. Stars like our Sun have moderate luminosity and stable habitable zones that can support life for billions of years. Planets within the habitable zones of G-type stars are prime candidates for Earth-like conditions. 2. Red dwarfs, M-type stars. Red dwarfs are smaller and cooler than the Sun, resulting in habitable zones that are much closer to the star. These stars are the most common in the galaxy, making them important targets in the search for habitable exoplanets. However, their high stellar activity, including frequent flares and radiation bursts, may pose challenges for life on nearby planets. Notable systems include TRAPPIST-1, with 7 Earth-sized planets, 3 of which lie in the habitable zone. 3. Blue giants and hot stars, O, B, and A-type stars. Larger, hotter stars have expansive habitable zones, but their lifespans are much shorter, often only a few million years, leaving little time for life to develop. Planets around these stars are less likely to be habitable over long periods. 4. Yellow dwarfs, K-type stars. Slightly smaller and cooler than the Sun, K-type stars offer stable, long-lived habitable zones. Planets orbiting these stars are promising targets for future missions. Expanding the definition of habitability. The traditional concept of the habitable zone focuses on surface liquid water, but recent discoveries suggest that habitability might extend beyond these narrow boundaries. Factors like subsurface oceans, atmospheric composition, and geothermal energy can create habitable conditions in unexpected places. 1. Subsurface oceans. Icy moons like Europa and Enceladus in our solar system have subsurface oceans beneath thick ice layers, kept warm by tidal heating. Similar conditions could exist on exoplanets or exomoons outside the traditional habitable zone. 2. Superhabitable planets. Some researchers propose the idea of superhabitable planets, worlds that might be even better suited for life than Earth. These planets could have slightly larger masses, warmer climates, and abundant water, creating more stable and diverse ecosystems. 3. runaway greenhouse and snowball Earth scenarios. Planets at the inner edge of the habitable zone may experience runaway greenhouse effects, like Venus, while those near the outer edge could enter snowball states, freezing over entirely. Understanding these extremes helps refine the search for habitable worlds. Tools for identifying habitable planets. Advances in astronomy have provided tools to identify and study planets within the habitable zones of their stars. These tools include 1. Space telescopes. Missions like Kepler, TESS, and the James Webb Space Telescope, JWST, have been instrumental in detecting exoplanets and characterizing their atmospheres. JWST, in particular, is capable of analyzing atmospheric composition for potential biosignatures, such as oxygen, methane, and water vapor. 2. Stellar spectroscopy. Observing the light from a planet's star during transits provides information about the planet's atmosphere and surface conditions. Spectroscopic data can reveal whether a planet lies within the habitable zone. 3. Climate modeling. Scientists use sophisticated climate models to simulate the conditions on exoplanets, accounting for factors like orbital eccentricity, axial tilt, and atmospheric composition. These models help refine the boundaries of the habitable zone for different star types. Exoplanets in the habitable zone. Key discoveries. Several exoplanets within their stars' habitable zones have captured the attention of scientists and the public alike. These planets, while diverse, share the potential to host liquid water. 1. Proxima Centauri b. Orbiting the closest star to our solar system, Proxima Centauri b lies within the habitable zone of its red dwarf star. Despite its proximity, the planet faces challenges such as stellar flares that could strip away its atmosphere. 2. Kepler 452b. Often referred to as Earth's cousin, this planet orbits a sun-like star in the habitable zone. Its larger size suggests it may be a super-Earth, though its exact conditions remain uncertain. 3. TRAPPIST-1 system. This remarkable system features 7 Earth-sized planets, 3 of which are in the habitable zone. Their proximity to one another creates dynamic interactions, making them ideal candidates for studying habitability. 4. LHS 1140b. A dense, rocky super-Earth in the habitable zone of a red dwarf star, LHS 1140b is considered one of the best candidates for studying atmospheric conditions and habitability. The challenges of defining habitability. While the concept of the habitable zone provides a useful framework, it is not without limitations. Life, as we understand it, relies on liquid water, but this assumption may exclude other forms of life that thrive in environments vastly different from Earth's. Additionally, planets within the habitable zone may lack other essential conditions for life, such as a protective magnetic field or a stable atmosphere. The search for biosignatures. One of the most exciting aspects of studying habitable zones is the potential detection of biosignatures, chemical markers that indicate biological activity. These markers might include oxygen, produced by photosynthetic organisms, though it can also arise from abiotic processes. Methane, a potential sign of microbial life when found alongside oxygen. Water vapor, an essential ingredient for life, detectable in planetary atmospheres. Upcoming missions and telescopes, such as the European Space Agency's Ariel and NASA's LUVOIR concept, aim to refine the search for biosignatures and expand our understanding of habitability. A universe of possibilities. The habitable zone represents more than just a scientific concept. It symbolizes humanity's enduring quest to find life among the stars. By exploring planets within these zones, we are not only searching for another Earth, but also testing the limits of our knowledge about life's resilience and adaptability. Whether life exists within these Goldilocks zones or in the most unexpected places, the journey to find it brings us closer to understanding our place in the cosmos. The habitable zone, where life could thrive. In the search for life beyond Earth, one concept has become central to our understanding of planetary habitability: the habitable zone. Often referred to as the Goldilocks zone, this is the region around a star where conditions might allow liquid water to exist on a planet's surface, neither too hot nor too cold. Water, being essential for all known life, serves as the foundation for defining this zone. The study of the habitable zone not only guides the search for potentially life-supporting exoplanets, but also deepens our understanding of what makes a planet capable of sustaining life. What is the habitable zone? The habitable zone is defined as the orbital region around a star where temperatures allow for liquid water to exist. The exact boundaries of this zone depend on the luminosity and type of the star, as well as the planet's atmospheric composition and other factors that influence its surface temperature. For example, inner boundary: too close to the star, a planet's surface becomes too hot, causing water to evaporate and potentially triggering a runaway greenhouse effect, as seen on Venus. Outer boundary: too far from the star, a planet's surface freezes, turning water into ice and making liquid water unlikely, as observed on Mars today. In our solar system, the habitable zone spans from just beyond Venus's orbit to slightly beyond Mars's orbit, with Earth sitting comfortably within this range. However, even within the habitable zone, other factors such as atmospheric pressure, greenhouse gas composition, and geological activity play critical roles in determining whether a planet can actually support life. Habitable zones around different types of stars. The habitable zone varies significantly depending on the type of star. Stars differ in size, temperature, and lifespan, which affect the extent and location of their habitable zones. 1. Sun-like stars, G-type stars. Stars like our Sun have moderate luminosity and stable habitable zones that can support life for billions of years. Planets within the habitable zones of G-type stars are prime candidates for Earth-like conditions. 2. Red dwarfs, M-type stars. Red dwarfs are smaller and cooler than the Sun, resulting in habitable zones that are much closer to the star. These stars are the most common in the galaxy, making them important targets in the search for habitable exoplanets. However, their high stellar activity, including frequent flares and radiation bursts, may pose challenges for life on nearby planets. Notable systems include TRAPPIST-1, with 7 Earth-sized planets, 3 of which lie in the habitable zone. 3. Blue giants and hot stars, O, B, and A-type stars. Larger, hotter stars have expansive habitable zones, but their lifespans are much shorter, often only a few million years, leaving little time for life to develop. Planets around these stars are less likely to be habitable over long periods. 4. Yellow dwarfs, K-type stars. Slightly smaller and cooler than the Sun, K-type stars offer stable, long-lived habitable zones. Planets orbiting these stars are promising targets for future missions, expanding the definition of habitability. The traditional concept of the habitable zone focuses on surface liquid water, but recent discoveries suggest that habitability might extend beyond these narrow boundaries. Factors like subsurface oceans, atmospheric composition, and geothermal energy can create habitable conditions in unexpected places. 1. Subsurface oceans. Icy moons like Europa and Enceladus in our solar system have subsurface oceans beneath thick ice layers, kept warm by tidal heating. Similar conditions could exist on exoplanets or exomoons outside the traditional habitable zone. 2. Superhabitable planets. Some researchers propose the idea of superhabitable planets, worlds that might be even better suited for life than Earth. These planets could have slightly larger masses, warmer climates, and abundant water, creating more stable and diverse ecosystems. 3. Runaway greenhouse and snowball Earth scenarios. Planets at the inner edge of the habitable zone may experience runaway greenhouse effects, like Venus, while those near the outer edge could enter snowball states, freezing over entirely. Understanding these extremes helps refine the search for habitable worlds. Tools for identifying habitable planets. Advances in astronomy have provided tools to identify and study planets within the habitable zones of their stars. These tools include: 1. Space telescopes. Missions like Kepler, TESS, and the James Webb Space Telescope (JWST) have been instrumental in detecting exoplanets and characterizing their atmospheres. JWST, in particular, is capable of analyzing atmospheric composition for potential biosignatures, such as oxygen, methane, and water vapor. 2. Stellar spectroscopy. Observing the light from a planet's star during transits provides information about the planet's atmosphere and surface conditions. Spectroscopic data can reveal whether a planet lies within the habitable zone. 3. Climate modeling. Scientists use sophisticated climate models to simulate the conditions on exoplanets, accounting for factors like orbital eccentricity, axial tilt, and atmospheric composition. These models help refine the boundaries of the habitable zone for different star types. Exoplanets in the habitable zone. Key discoveries. Several exoplanets within their stars' habitable zones have captured the attention of scientists and the public alike. These planets, while diverse, share the potential to host liquid water. 1. Proxima Centauri b. Orbiting the closest star to our solar system, Proxima Centauri b lies within the habitable zone of its red dwarf star. Despite its proximity, the planet faces challenges such as stellar flares that could strip away its atmosphere. 2. Kepler 452b. Often referred to as Earth's cousin, this planet orbits a sun-like star in the habitable zone. Its larger size suggests it may be a super-Earth, though its exact conditions remain uncertain. 3. TRAPPIST-1 system. This remarkable system features 7 Earth-sized planets, 3 of which are in the habitable zone. Their proximity to one another creates dynamic interactions, making them ideal candidates for studying habitability. 4. LHS 1140b. A dense, rocky super-Earth in the habitable zone of a red dwarf star, LHS 1140b is considered one of the best candidates for studying atmospheric conditions and habitability. The challenges of defining habitability. While the concept of the habitable zone provides a useful framework, it is not without limitations. Life, as we understand it, relies on liquid water, but this assumption may exclude other forms of life that thrive in environments vastly different from Earth's. Additionally, planets within the habitable zone may lack other essential conditions for life, such as a protective magnetic field or a stable atmosphere. The search for biosignatures. One of the most exciting aspects of studying habitable zones is the potential detection of biosignatures, chemical markers that indicate biological activity. These markers might include oxygen, produced by photosynthetic organisms, though it can also arise from abiotic processes. Methane, a potential sign of microbial life when found alongside oxygen. Water vapor, an essential ingredient for life, detectable in planetary atmospheres. Upcoming missions and telescopes, such as the European Space Agency's Ariel and NASA's LUVOIR concept, aim to refine the search for biosignatures and expand our understanding of habitability. A universe of possibilities. The habitable zone represents more than just a scientific concept. It symbolizes humanity's enduring quest to find life among the stars. By exploring planets within these zones, we are not only searching for another Earth, but also testing the limits of our knowledge about life's resilience and adaptability. Whether life exists within these Goldilocks zones or in the most unexpected places, the journey to find it brings us closer to understanding our place in the cosmos. Water worlds and ocean planets. In the vast diversity of exoplanets, one type captures the imagination with its potential to host life: water worlds or ocean planets. These enigmatic worlds are thought to be covered almost entirely by vast, global oceans, spanning thousands of kilometers in depth and enveloping their entire surfaces. Free from the constraints of continents and land masses, these planets offer unique insights into planetary evolution, the potential for alien ecosystems, and the resilience of life in extreme environments. This chapter dives into the characteristics, formation, and habitability of these oceanic worlds, as well as their significance in the search for life beyond Earth. What are water worlds? Water worlds are planets where water dominates the surface, forming global oceans that may be tens to hundreds of kilometers deep. Unlike Earth, where oceans are interrupted by continents and islands, water worlds have no significant land masses. Their surfaces are entirely liquid, or in some cases, covered with a layer of ice, depending on their proximity to their host star. Water worlds can range in size and composition, often classified into 2 broad categories. 1. Rocky water worlds. These planets have a solid, rocky core surrounded by a thick layer of water and may include Earth-like atmospheric conditions. 2. Icy ocean planets. These are typically farther from their stars and feature a frozen outer layer covering a subsurface ocean kept warm by internal heat. How do water worlds form? The formation of water worlds begins in the early stages of planetary system development, within protoplanetary disks rich in water ice and other volatiles. Key processes in their creation include 1. Formation beyond the frost line. Water worlds are believed to form beyond the frost line, the distance from a star where temperatures are low enough for water to condense into ice. In this region, planets accumulate large amounts of water ice, which melts into liquid as the planet migrates closer to the star or remains solid in colder orbits. 2. Accretion of volatiles. During planetary formation, water-rich material is incorporated into the growing planet. The proportion of water compared to rock and metal determines whether the planet will become a water world. 3. Planetary migration. Many water worlds are thought to migrate inward from their formation zones beyond the frost line. During this migration, they retain their water content, resulting in worlds with vast oceans even in warmer regions closer to their stars. Characteristics of water worlds. Water worlds possess unique physical and chemical properties that set them apart from other planetary types. These characteristics include 1. Global oceans. The oceans on water worlds may be thousands of kilometers deep, dwarfing Earth's oceans, which average just 4 kilometers in depth. Beneath these oceans, immense pressure creates layers of exotic forms of water, such as high-pressure ice, Ice 7, or Ice X. 2. Thick atmospheres. Water worlds often have thick atmospheres composed of water vapor, hydrogen, and other volatiles. The greenhouse effect from these atmospheres can create warm, stable conditions for liquid water. 3. Internal heating. Many water worlds experience internal heating due to radioactive decay or tidal forces, which can sustain subsurface oceans even on planets with frozen surfaces. 4. Varied surface conditions. Depending on their distance from the star, water worlds may have liquid surfaces, frozen crusts, or combinations of both. Some planets, like icy moons in our solar system, exhibit active water plumes that erupt from subsurface oceans. Potential habitability of water worlds. The presence of liquid water is a cornerstone of habitability as we understand it. On water worlds, the abundance of water creates unique environments that could support life. Key factors influencing habitability include 1. Stable oceans. Global oceans provide a consistent and stable environment for life to evolve. Unlike land-based ecosystems, oceanic habitats are less affected by temperature fluctuations and extreme weather. 2. Nutrient cycling. Life requires more than just water. It also needs nutrients and energy sources. On water worlds, volcanic activity on the seafloor could release essential minerals, while chemical gradients in the oceans may drive energy cycles similar to those on Earth. 3. Subsurface oceans. On icy water worlds, subsurface oceans insulated by thick ice layers may offer protection from stellar radiation and harsh surface conditions. These environments could mimic the conditions of Earth's deep ocean hydrothermal vents, where life thrives without sunlight. Analogs in our solar system. Our solar system offers compelling examples of potential water worlds, providing valuable analogs for understanding these planets. 1. Europa, moon of Jupiter. Europa is covered by a thick layer of ice, beneath which lies a subsurface ocean. Tidal heating from Jupiter's gravitational pull keeps the ocean liquid, making Europa one of the most promising candidates for life in our solar system. 2. Enceladus, moon of Saturn. Enceladus, another icy moon, has a subsurface ocean that occasionally erupts through cracks in the ice, creating water plumes. These plumes contain organic molecules, further heightening its potential for habitability. 3. Ganymede and Callisto, moons of Jupiter. Both moons are believed to have subsurface oceans, though they are buried beneath thicker ice layers compared to Europa. 4. Titan, moon of Saturn. Titan, with its lakes and seas of liquid methane and ethane, presents a different type of water world. While it lacks liquid water on the surface, its subsurface may host a water ammonia ocean. Exoplanetary water worlds. Key discoveries. Recent observations have identified several exoplanets that may qualify as water worlds. While direct confirmation is challenging, these planets exhibit characteristics consistent with oceanic environments. 1. GJ-1214b, a mini-Neptune with a thick atmosphere rich in water vapor. GJ-1214b is a leading candidate for being a water world. 2. K2-18b. This super-Earth in the habitable zone of its star shows evidence of water vapor in its atmosphere, raising the possibility of a global ocean. 3. TOI-1452b. A recently discovered super-Earth that scientists believe could be covered entirely by water, based on its density and orbit. 4. TRAPPIST-1 system. Several planets in this system are thought to have significant water content, particularly those in the habitable zone. Challenges in detecting water worlds. Identifying water worlds is a complex task, as their characteristics can be easily mistaken for those of other types of planets. Challenges include atmospheric analysis. Distinguishing between water vapor and other compounds in a planet's atmosphere requires precise spectroscopy. Mass and density ambiguity. A planet's mass and radius provide clues about its composition, but similar values can correspond to rocky planets, gas-rich mini-Neptunes, or water worlds. Cloud cover. Thick clouds can obscure a planet's surface, complicating efforts to study its oceans. The role of future missions. Upcoming telescopes and missions promise to advance our understanding of water worlds. The James Webb Space Telescope (JWST) is already analyzing the atmospheres of potentially water-rich exoplanets. Future projects like Ariel and the LUVOIR concept aim to refine atmospheric studies, while ground-based observatories will complement these efforts with high-resolution imaging. The significance of water worlds. Water worlds represent one of the most promising avenues in the search for extraterrestrial life. Their abundance of water, stable environments, and potential for diverse ecosystems make them ideal candidates for hosting life as we know it, or even life forms entirely different from those on Earth. As we continue to explore the universe, these ocean planets remind us of the boundless possibilities that exist within the cosmos. In the ever-expanding catalog of exoplanets, some worlds stand out not for their potential to harbor life, but for the extreme conditions that define their existence. Among these are lava worlds, planets so close to their stars that their surfaces are transformed into molten landscapes of fire and brimstone. These infernal worlds challenge our understanding of planetary composition and behavior, revealing a side of the cosmos where the laws of physics are pushed to their limits. Lava worlds typically orbit their stars at blistering proximity, often completing a full revolution in just a few days. This closeness exposes them to intense stellar radiation, heating their surfaces to thousands of degrees. Rocky planets in such environments cannot maintain solid crusts. Instead, their surfaces become oceans of molten rock, constantly reshaped by tidal forces and volcanic activity. The discovery of these planets has been driven by advances in observational techniques, particularly the transit method and spectroscopy. When a lava world transits its star, the starlight passing through its superheated atmosphere can carry signatures of vaporized rock, such as silicates and metal oxides. These unique chemical fingerprints provide valuable clues about the planet's composition and the extreme processes shaping it. One of the most famous lava worlds is 55 Cancri, a planet twice the size of Earth orbiting its star at an incredible distance of just 0.016 Australian dollars, less than 1/25th of the distance from Mercury to the Sun. Its surface temperatures exceed 2,400 Kelvin, hot enough to vaporize rock. Observations suggest that one side of the planet remains perpetually molten, facing the star in a state of tidal locking, while the other side may be slightly cooler, potentially solidifying into a crust. This stark dichotomy offers a glimpse into the dynamics of such extreme environments. Lava worlds also raise fascinating questions about planetary formation and evolution. Their close orbits defy conventional models of planetary system development, as rocky planets are generally thought to form farther from their stars, where temperatures are lower. The existence of these molten infernos suggests that migration plays a critical role, with planets moving inward over time due to gravitational interactions with their protoplanetary disks or neighboring planets. Once settled in their scorching orbits, these worlds undergo dramatic transformations. Stellar radiation strips away lighter elements, leaving behind dense, rocky cores. The intense heat and tidal forces can also drive volcanic activity on an unprecedented scale, reshaping the planet's surface over time. Despite their hostile conditions, lava worlds provide a unique opportunity to study the behavior of materials under extreme heat and pressure. Their molten surfaces act as laboratories for understanding the properties of rock vapor and the atmospheric dynamics of superheated gases. By studying these planets, scientists can refine models of planetary interiors and gain insights into the processes that shaped rocky worlds, including Earth, during their early histories. One intriguing aspect of lava worlds is the potential for exotic weather systems. At extreme temperatures, elements like silicon and iron can vaporize, forming metallic clouds and even rain composed of molten rock. Winds on these planets could redistribute heat and materials, creating dynamic atmospheric patterns unlike anything seen on Earth. Observing these phenomena not only expands our understanding of planetary climates, but also highlights the diversity of conditions under which planets can exist. While lava worlds are unlikely to harbor life, their study holds significant implications for exoplanet science. They serve as examples of planetary extremes, testing the boundaries of what is possible in the cosmos. Moreover, they offer a stark contrast to more temperate, potentially habitable worlds, enriching our perspective on the diversity of planetary systems. The exploration of lava worlds is still in its infancy, but the potential for discovery is immense. Future telescopes equipped with advanced spectroscopic capabilities will provide more detailed observations of these planets, unraveling their mysteries and shedding light on the processes that govern their evolution. As we continue to search the skies, these fiery worlds remind us of the cosmos's untamed creativity, where even the most inhospitable environments tell stories of resilience and transformation. The universe, vast and unpredictable, offers a stage where worlds of unparalleled extremes coexist with those that echo the familiar. In this cosmic theater, each discovery of an exoplanet presents a new chapter in understanding the possibilities of planetary existence. Among these discoveries are atmospheres that defy our expectations, revealing hidden stories about the nature of distant worlds. The study of exoplanet atmospheres is not merely a quest for data. It is a journey into understanding how planets interact with their stars, how their chemical compositions evolve, and, perhaps most tantalizingly, whether they can support life. Atmospheres serve as both the shields and mirrors of their planets, protecting them from the harshness of space while reflecting the signatures of their environments back to observers. On Earth, the atmosphere is a delicate balance of nitrogen, oxygen, carbon dioxide, and trace gases, each playing a role in sustaining life. The atmospheres of exoplanets, however, are as varied as the planets themselves, ranging from dense, crushing envelopes of hydrogen and helium to thin, tenuous layers of exotic molecules. Each atmospheric signature offers a clue, a piece of a larger puzzle, about the planet's history, its potential for habitability, or the violent processes that have shaped it. For astronomers, detecting and studying these atmospheres requires ingenuity. Light is the primary messenger from these distant worlds. When a planet passes in front of its host star, some of the starlight filters through the planet's atmosphere. This light carries with it a wealth of information about the atmospheric composition, encoded in the form of absorption lines, specific wavelengths of light absorbed by molecules in the atmosphere. Through a technique known as transmission spectroscopy, scientists can analyze these fingerprints to identify the gases present and even infer temperature and pressure conditions. The James Webb Space Telescope has revolutionized this field, offering unprecedented sensitivity for observing the atmospheres of smaller, rocky exoplanets in addition to the more massive gas giants. For example, water vapor, carbon dioxide, methane, and oxygen, all potential indicators of habitability or biological activity, can now be detected and analyzed with remarkable precision. Even clouds and hazes, long considered obstacles to clear observations, provide valuable information about atmospheric dynamics and climate. In the realm of gas giants, atmospheres are often dense and tumultuous, reflecting the chaotic environments close to their host stars. Hot Jupiters, for instance, exhibit atmospheres so heated that metals vaporize, forming clouds of exotic substances. The presence of titanium oxide, water vapor, and silicates has been observed in these scorching worlds, revealing chemistry far removed from anything familiar. Winds on these planets can reach thousands of kilometers per hour, redistributing heat and sculpting the atmospheric landscape. Meanwhile, the atmospheres of smaller worlds, such as super-Earths and mini-Neptunes, remain enigmatic. These planets often straddle the line between rocky and gaseous, their atmospheres varying from thick blankets of hydrogen and helium to secondary atmospheres formed from volcanic outgassing or impacts. For rocky planets, the presence of elements like nitrogen, oxygen, and water vapor hints at the possibility of surface conditions conducive to life. However, even with the most advanced instruments, distinguishing between life-supporting atmospheres and those formed by abiotic processes remains a challenge. Some of the most intriguing observations come from planets in the habitable zones of their stars. These planets, positioned at the delicate balance point where liquid water might exist, are the focus of intense scrutiny. Atmospheric studies of such planets aim to identify biosignatures, chemical markers that could indicate biological activity. The simultaneous presence of oxygen and methane, for instance, is difficult to sustain without biological processes, as these gases would otherwise react and neutralize each other. Detecting such combinations could provide the first indirect evidence of extraterrestrial life. In some cases, exoplanet atmospheres tell stories of violence and loss. Stellar radiation and winds can strip away lighter gases, leaving behind heavier elements or rendering the planet barren. This process, known as atmospheric escape, is particularly pronounced in close-in planets subjected to intense stellar activity. Understanding these processes not only reveals the vulnerabilities of planetary atmospheres, but also highlights the resilience of those that endure. The study of exoplanet atmospheres also offers a window into planetary formation and migration. By analyzing the ratios of elements such as carbon and oxygen, scientists can infer where in the protoplanetary disk a planet formed and how its journey through the disk influenced its composition. These insights help refine models of planetary evolution, providing a broader context for the diversity of planetary systems observed today. As technology advances, the ability to probe deeper into the atmospheres of distant worlds will expand. Missions like Ariel and proposed concepts like LUVOIR promise to deepen our understanding, targeting planets with increasing precision and aiming to answer fundamental questions about their potential for life. Yet, for all the progress made, the study of exoplanet atmospheres is still in its infancy, with each observation serving as a stepping stone toward uncovering the secrets of worlds beyond. In these atmospheres, the boundaries of the possible stretch before us. Whether revealing the harshness of molten skies, the dynamism of turbulent clouds, or the whispers of potential habitability, they remind us that the universe is more varied and complex than we ever imagined. Each new discovery brings us closer to understanding not just the planets themselves, but also the intricate interplay of forces that shape them, and, by extension, the forces that have shaped our own planet and life as we know it. The exploration of the cosmos through the lens of exoplanetary studies often leads to questions that bridge science and philosophy. Where does life arise, and under what conditions might it thrive? Among the myriad stars and their orbiting planets, astronomers are narrowing their focus on worlds that hold the greatest potential to answer this question. At the heart of this quest lies the concept of biosignatures, those elusive chemical and physical markers that hint at or confirm the presence of life. Biosignatures encompass a wide range of phenomena, from molecular traces in planetary atmospheres to surface features visible from afar. The search for these markers is driven by a fundamental assumption. Life, as we understand it, alters its environment in detectable ways. On Earth, for instance, oxygen in the atmosphere, a byproduct of photosynthesis, coexists with methane, a gas that would not naturally persist alongside oxygen without continuous biological replenishment. Together, these gases form a signature of life, one that scientists aim to detect on distant exoplanets. The tools used to identify biosignatures are among the most advanced in modern astronomy. Transmission spectroscopy, wherein light from a host star passes through a planet's atmosphere during a transit, allows scientists to decode the atmospheric composition. Reflected light from a planet's surface, when analyzed, can reveal the presence of pigments such as chlorophyll, indicative of photosynthetic processes. Even the thermal emissions of a planet can provide clues about its surface and atmospheric chemistry. One of the most exciting aspects of biosignature research is its potential to redefine our understanding of life. While Earth-centric models dominate current thinking, scientists recognize the possibility of exotic biospheres with life forms that do not rely on the same chemical processes as terrestrial organisms. On Titan, a moon of Saturn, for instance, lakes and seas of methane and ethane might support life that uses hydrocarbons as a solvent rather than water. Exoplanets with high concentrations of sulfur or ammonia could similarly host life forms adapted to such environments. These possibilities compel researchers to think beyond the boundaries of Earth's biology. Despite the promise of biosignatures, interpreting them is fraught with challenges. Many processes that mimic life can produce similar chemical markers. Oxygen, for example, can be generated abiotically through photodissociation of water vapor, and methane can result from volcanic activity or hydrothermal processes. Distinguishing between biological and non-biological sources requires not only precise measurements, but also an understanding of the planet's broader environmental context. This context includes the influence of the host star, which plays a crucial role in shaping a planet's habitability and biosignature potential. Red dwarfs, for instance, emit less visible light but produce intense ultraviolet radiation, which can break down atmospheric molecules and complicate the detection of biosignatures. Conversely, stars with stable luminosities and longer lifespans, like K-type and G-type stars, provide conditions more conducive to life as we understand it, making their planets prime targets for biosignature research. The study of biosignatures also extends to surface features and planetary geology. Seasonal changes in vegetation on Earth, observable through variations in reflected light, could have analogs on distant worlds. Similarly, the presence of liquid water, visible through specular reflections or glints, would provide compelling evidence of a key ingredient for life. These features are particularly challenging to detect, requiring advanced imaging techniques that can distinguish the faint light of a planet from the overwhelming glare of its star. As astronomers refine their methods, certain exoplanets have emerged as particularly intriguing candidates for biosignature detection. Proxima Centauri b, despite its exposure to stellar flares, lies in the habitable zone of the closest star to the Sun, offering a unique opportunity for study. The TRAPPIST-1 system, with its 7 Earth-sized planets, 3 of which reside in the habitable zone, has captivated researchers with its potential for atmospheric characterization. Kepler 452b, often referred to as a super-Earth, resides in the habitable zone of a Sun-like star and offers conditions that may resemble those of early Earth. Future missions are poised to push the search for biosignatures to new heights. The James Webb Space Telescope, with its unparalleled sensitivity to infrared light, is already beginning to analyze the atmospheres of potentially habitable exoplanets. Upcoming projects like the European Space Agency's Ariel mission and NASA's HabEx and LUVOIR concepts promise to refine our ability to detect and analyze biosignatures, targeting planets that represent the most likely hosts for life. The implications of detecting a biosignature are profound, reaching far beyond the realms of science. The confirmation of extraterrestrial life would forever alter our understanding of the universe and our place within it. It would raise questions about the origins and diversity of life, the potential for communication, and the philosophical and ethical considerations of our interactions with alien ecosystems. Yet, the search for biosignatures is as much about the journey as the destination. Every step in this quest deepens our appreciation for the complexity and diversity of planetary systems. It reveals the delicate interplay of forces that make a planet habitable and underscores the resilience of life in the face of seemingly insurmountable odds. Each discovery, whether it confirms life or reveals another piece of the cosmic puzzle, brings us closer to answering the age-old question: are we alone? The universe, in its infinite complexity, offers no shortage of phenomena to explore. As our understanding of exoplanets deepens, the focus often shifts from individual planets to the intricate relationships within their systems. One of the most captivating configurations involves exoplanets orbiting binary or multi-star systems. These celestial dances, where planets are caught between the gravitational pull of two or more stars, challenge our understanding of planetary formation and dynamics while expanding the boundaries of what is considered possible. Binary and multi-star systems are more common than single-star systems like our own. Roughly half of all stars in the galaxy exist in binary pairs or larger groups, making these systems a significant arena for exoplanetary research. The discovery of planets within these systems initially seemed improbable, given the complex gravitational interactions that might disrupt planetary orbits. Yet, observations have revealed that planets not only form in such systems, but often thrive in configurations previously thought unstable. Planets in binary systems typically follow one of two orbital paths. In a circumbinary orbit, the planet orbits both stars at a sufficient distance that the pair acts as a single gravitational entity. These configurations evoke comparisons to the fictional Tatooine of Star Wars, where a double sunset graces the horizon. Observations of circumbinary planets like Kepler-16b confirm the viability of such orbits, with stable conditions allowing the planet to maintain its trajectory over billions of years. The second configuration involves circumstellar orbits, where a planet orbits one star while the second star remains more distant. These systems are more similar to our own, albeit with the added gravitational influence of a secondary star. Circumstellar planets, such as those observed in the Alpha Centauri system, demonstrate the resilience of planetary systems even in the presence of significant gravitational perturbations. The formation of planets in binary systems presents a unique set of challenges and opportunities. In circumbinary configurations, the gravitational forces of the two stars create a dynamic environment in the protoplanetary disk. Despite these challenges, evidence suggests that disk fragmentation and the accumulation of planetesimals can proceed effectively, leading to the formation of planets. In circumstellar configurations, the secondary star's influence can shepherd material within the disk, shaping planetary orbits and potentially enhancing the efficiency of planet formation. The habitability of planets in binary systems is a subject of particular interest. Circumbinary planets, for instance, must reside within a stable orbit that avoids gravitational chaos while maintaining a location conducive to liquid water. The interplay of stellar luminosities can create unique habitable zones, where the combined heat and light from both stars sustain life-friendly conditions. Circumstellar planets face their own challenges, such as variable radiation levels and orbital perturbations, which can influence climate stability. Among the most intriguing aspects of binary systems is their potential for fostering diverse planetary environments. A planet orbiting a single star in a wide binary system may experience gravitational influences that tilt its axis, alter its orbit, or even trigger episodes of planetary migration. These dynamics can produce climates and geological activity unlike anything seen in our solar system, adding to the rich tapestry of planetary possibilities. Multi-star systems, which involve three or more stars, take this complexity to another level. Planets in such systems must navigate a gravitational maze, with stability depending on precise configurations. Despite these challenges, discoveries like the planet in the triple star system, HD 188753, reveal the remarkable adaptability of planetary systems. These configurations highlight the tenacity of planets, which seem to find stable niches even in environments dominated by chaos. The study of planets in binary and multi-star systems offers profound insights into the adaptability of planetary formation processes. By understanding how planets survive and thrive in these environments, scientists can refine models of planetary evolution and extend their search for habitable worlds. The presence of two or more stars in a system also provides additional opportunities for studying planetary atmospheres, as light from multiple sources can illuminate different layers of the atmosphere during transits. Future telescopes and missions are poised to revolutionize our understanding of these systems. Projects like the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope will offer unparalleled resolution for studying binary and multi-star systems, enabling detailed observations of their planets' atmospheres, orbits, and compositions. These advancements will help answer fundamental questions about the limits of habitability and the conditions under which planets can form and endure. The discovery of planets in binary and multi-star systems underscores the universe's capacity for complexity and resilience. It challenges our assumptions about the boundaries of habitability and planetary stability, revealing a cosmos where planets and stars weave intricate tapestries of gravitational harmony. As we continue to explore these celestial systems, they serve as a reminder that even in the most challenging environments, the universe finds ways to create and sustain worlds. The universe is a realm of extremes, and as astronomers uncover the secrets of exoplanets, some worlds defy not only expectations, but also the very definitions of what planets can be. Among the most bizarre discoveries are planets so strange, so alien, that they challenge the limits of our imagination. These peculiar worlds, some shimmering with diamond-like surfaces, others raining molten glass, reveal the unbridled creativity of cosmic processes and the boundless variety of planetary environments. One of the most famous examples of an extraordinary planet is 55 Cancri, a world that orbits its star so closely it completes a year in just 18 hours. This proximity heats its surface to extreme temperatures, creating a molten landscape. What sets 55 Cancri apart, however, is its potential composition. Observations suggest it may be rich in carbon, leading to speculation that its interior could host diamond layers formed under intense pressure. If true, 55 Cancri would be a literal gem in the galaxy, a world where geological processes create wealth on a planetary scale. Another extraordinary planet, HD 189733b, is a gas giant that captures attention with its weather systems. Winds on this planet reach speeds of over 8,000 kilometers per hour, driving storms that dwarf the largest hurricanes on Earth. Even more astonishing is the planet's weather. Its atmosphere contains silicate particles, which, under the intense heat, form clouds that rain molten glass sideways. The combination of high winds and glass rain creates a landscape as dangerous as it is fascinating, highlighting the wild extremes of atmospheric physics. Kepler-10c, often referred to as a mega-Earth, is another anomaly. This rocky planet is 17 times the mass of Earth, but has a composition similar to terrestrial worlds. Its sheer size challenges models of planetary formation, which suggests that a planet of this mass should have accumulated a thick atmosphere and become a gas giant. Kepler-10c's existence forces scientists to reconsider the processes that govern planet formation and raises questions about the upper limits of rocky worlds. In the colder reaches of the cosmos, another category of unusual planets exists: rogue planets. These free-floating worlds drift through interstellar space, unbound by any star. Rogue planets likely form within planetary systems, but are ejected during gravitational interactions. Some may even form directly from collapsing clouds of gas, much like stars. Despite their isolation and the absence of stellar warmth, rogue planets may harbor subsurface oceans heated by radioactive decay, offering potential refuges for life in the cold void of space. Not all strange planets are far removed from Earth's characteristics. Some, like K2-18b, blur the line between habitable and inhospitable. This super-Earth resides in the habitable zone of its star and shows signs of water vapor in its atmosphere. However, its thick gaseous envelope and high pressure may make its surface unsuitable for life as we know it. These hybrid worlds, neither fully rocky nor entirely gaseous, challenge our binary thinking about planetary categories and demand new frameworks for understanding habitability. Planets with extreme orbits further expand the spectrum of strange worlds. HD 80606b, for example, follows a highly eccentric orbit that brings it perilously close to its star before swinging back into the cold reaches of its system. This journey subjects the planet to drastic temperature swings, creating a dynamic climate where entire hemispheres heat up and cool down within days. Such planets offer natural laboratories for studying the effects of extreme stellar radiation and rapid atmospheric changes. Even within the realm of gas giants, there are planets that defy expectations. WASP-12b is a hot Jupiter so close to its star that it is being tidally distorted, pulling its shape into an elongated ellipsoid. Over time, the star's gravity is stripping material from the planet, creating a stream of gas that spirals into the star. This slow disintegration provides a unique glimpse into the fate of planets in extreme environments. Among the strangest phenomena are planets that might not even fit traditional definitions. PSRB 1620-26b, nicknamed the Methuselah planet, is one of the oldest known exoplanets, dating back nearly 13 billion years. Orbiting a binary system composed of a pulsar and a white dwarf, this planet exists in an environment shaped by the remnants of supernovae and stellar evolution. Its age and survival challenge assumptions about planetary lifespans and the conditions required for their stability. These extraordinary planets serve as reminders that the universe is not constrained by the familiar. They push the boundaries of planetary science, forcing researchers to expand theoretical models and embrace new possibilities. As detection techniques improve, even stranger worlds are likely to emerge, each with unique properties and stories to tell. The study of these outliers has profound implications. They provide critical data points that test the robustness of planetary formation theories and offer insights into the physical processes that govern extreme environments. Moreover, they inspire deeper philosophical questions about the diversity of planetary systems and the potential for life in forms vastly different from those on Earth. In the cosmic tapestry, these strange and extraordinary planets are the rare, vivid threads that stand out against the backdrop of more conventional worlds. They remind us that the universe's creativity knows no bounds, and that every discovery, no matter how alien, enriches our understanding of the cosmos. As the boundaries of planetary science continue to expand, one frontier offers both mystery and boundless potential: the search for moons orbiting exoplanets. These celestial companions, known as exomoons, could be just as diverse and intriguing as the planets they orbit. While no exomoon has yet been definitively confirmed, the search for these elusive bodies is one of the most exciting areas in astronomy, with implications that stretch from understanding planetary systems to the potential for life. Moons in our solar system reveal the incredible variety that such worlds can exhibit. From the volcanic activity of Io to the icy oceans of Europa, the methane lakes of Titan, and the geysers of Enceladus, moons have shown themselves to be dynamic, geologically active, and, in some cases, potentially habitable. If such diversity exists among the moons of our solar system, it is likely mirrored in the exomoons orbiting planets throughout the galaxy. Exomoons are expected to form in much the same way as moons in our solar system, through three primary mechanisms. Some are formed alongside their planets in the protoplanetary disk, coalescing from the material left over after the planet's formation. Others are captured objects, such as asteroids or smaller planets, pulled into orbit by the planet's gravity. A third group, the product of massive impacts, includes moons like Earth's own, formed when a collision ejected material into orbit that later coalesced. Detecting exomoons is a significant observational challenge. Unlike planets, which can be detected through their effects on their host stars, exomoons are smaller, dimmer, and harder to observe directly. Astronomers rely on indirect methods, such as monitoring the slight variations in a planet's transit timing or brightness, caused by the gravitational tug of an orbiting moon. These techniques require extraordinary precision and often depend on long-term observations to detect the faint signals of a moon's presence. The potential for habitability on exomoons adds a layer of excitement to their search. A moon orbiting within the habitable zone of its star, even if its planet is uninhabitable, could host conditions suitable for life. Such a moon might benefit from tidal heating, a process where the gravitational pull of its planet generates internal heat, allowing liquid water to exist even in regions far from the warmth of a star. In some cases, moons could inherit protective magnetic fields from their planets, shielding them from harmful radiation. The concept of habitable exomoons also raises intriguing possibilities for environments that differ significantly from Earth. A moon with a thick atmosphere could support unique weather patterns and climates, while an icy exomoon with a subsurface ocean might harbor ecosystems akin to those found near hydrothermal vents on Earth. These moons expand the definition of habitability, showing that life could thrive in environments far removed from the surface-based ecosystems we are familiar with. One candidate for an exomoon, Kepler 1625 b, has sparked significant interest. Orbiting a giant planet in the habitable zone of its star, this potential exomoon is thought to be Neptune-sized, far larger than any moon in our solar system. If confirmed, its discovery would not only prove the existence of exomoons, but also suggest that moons can grow to sizes previously thought improbable, offering even more opportunities for varied and complex environments. Exomoons also play a critical role in understanding the dynamics of planetary systems. Their interactions with their host planets can influence orbital stability, migration, and even atmospheric retention. By studying these interactions, astronomers gain insights into the broader processes that govern planetary formation and evolution. The search for exomoons is entering a new era with the advent of advanced telescopes and observation techniques. Instruments like the James Webb Space Telescope are capable of analyzing the faint signals associated with potential exomoons, while future missions like LUVOIR and the Nancy Grace Roman Space Telescope promise even greater precision. These technologies bring the prospect of discovering and studying exomoons within reach, potentially opening a new chapter in our exploration of the cosmos. Exomoons, when confirmed, will undoubtedly enrich our understanding of planetary systems and the diversity of worlds that populate the galaxy. They will challenge us to reconsider the conditions under which life might arise and the roles moons play in shaping the environments of their host planets. Above all, they will remind us that the cosmos is far more complex and interconnected than we can yet imagine, offering new mysteries to unravel and new frontiers to explore. As the quest for knowledge extends further into the cosmos, the role of artificial intelligence and machine learning emerges as a powerful ally in the discovery and analysis of exoplanets. The staggering volume of data collected by space telescopes like Kepler, TESS, and the James Webb Space Telescope exceeds what traditional methods can process efficiently. This is where advanced computational tools step in, revolutionizing the pace and precision of exoplanet research. AI, at its core, excels at pattern recognition, a capability perfectly suited for sifting through the immense datasets generated by astronomical surveys. For exoplanet detection, machine learning algorithms analyze light curves, graphs of a star's brightness over time, searching for the subtle dips that indicate a planet transiting its star. These dips, often obscured by noise from stellar activity or instrument sensitivity, are identified with remarkable accuracy by AI systems trained on thousands of examples. One of the key breakthroughs in AI-assisted exoplanet discovery came with the reanalysis of Kepler data. Traditional methods, while effective, left some planetary signals undetected, buried within the noise. Machine learning algorithms developed specifically for this purpose uncovered dozens of previously unnoticed exoplanets, demonstrating the transformative potential of AI. Among these discoveries were Earth-sized planets in their stars' habitable zones, emphasizing the importance of revisiting data with improved techniques. Beyond detection, AI plays a critical role in characterizing exoplanets. Algorithms can classify planets based on their size, orbital period, and host star properties, streamlining the process of identifying candidates for detailed study. For instance, systems trained to recognize patterns associated with different planetary types, such as gas giants, rocky worlds, or water-rich planets, can quickly sort through datasets, prioritizing targets for atmospheric analysis or further observation. One of the most exciting applications of AI lies in the search for biosignatures. By analyzing spectral data from planetary atmospheres, machine learning models can identify the presence of gases like oxygen, methane, and water vapor. These algorithms are not limited to known patterns. They can be trained to detect combinations of elements that suggest habitability or even the potential for life. As telescopes grow more sensitive, AI will become indispensable in parsing the increasingly complex data required to identify these subtle signals. AI's impact extends to refining our understanding of planetary systems as a whole. Simulations powered by machine learning help model the formation and evolution of exoplanetary systems, accounting for the interactions between planets, stars, and disks of gas and dust. These models provide insights into the processes that shape planetary diversity, from migration patterns to atmospheric development. Collaboration between AI and astronomers is not a one-sided affair. While AI systems bring speed and precision, human expertise remains essential for interpreting findings and ensuring accuracy. The iterative process of training machine learning models relies on astronomers to label and verify data, creating feedback loops that continuously improve the algorithms. This synergy highlights the balance between computational power and human intuition, each complementing the other. The role of AI in exoplanet research also pushes the boundaries of how we approach scientific discovery. Traditional methods often rely on hypothesis-driven exploration, where researchers seek answers to specific questions. AI, however, thrives in data-driven environments, uncovering correlations and patterns that humans might not think to investigate. This paradigm shift expands the scope of what can be studied, opening pathways to discoveries previously beyond our reach. As AI becomes more integrated into exoplanetary science, its potential continues to grow. Future advancements in quantum computing and neural networks promise to further accelerate data analysis, enabling the detection of smaller, more distant planets and the characterization of their atmospheres. Meanwhile, AI-powered telescopes and autonomous observation systems may one day conduct their own surveys, selecting targets and adjusting instruments in real time based on observed data. The impact of AI extends beyond the immediate goal of finding exoplanets. By enhancing our ability to analyze and interpret data, it contributes to the broader mission of understanding the cosmos. Each discovery, whether of a potentially habitable planet or an entirely unexpected type of world, adds a piece to the puzzle of our existence, illuminating the forces that shape the universe and the possibilities it holds. Artificial intelligence is not just a tool, but a partner in exploration. It represents the fusion of human ingenuity and technological innovation, driving us closer to answering the fundamental questions of who we are and whether we are alone. As we continue to integrate AI into our search for exoplanets, the horizon of discovery stretches ever further, offering endless possibilities for what we might uncover next. The search for exoplanets is as much a journey into the unknown as it is an exploration of the forces that shape planetary systems. At the heart of this quest lies the need to understand how planets form and evolve, a process that begins in the swirling disks of gas and dust surrounding young stars. These protoplanetary disks, the birthplaces of planets, offer a window into the mechanics of creation, revealing how particles coalesce to form worlds and the dynamic forces that influence their eventual fates. Planet formation begins with the collapse of a molecular cloud, a vast region of interstellar gas and dust. As gravity pulls the material inward, it forms a spinning disk around a nascent star. Within this disk, minute particles collide and stick together, growing into larger aggregates. Over time, these particles form planetesimals, building blocks of planets ranging from a few kilometers to hundreds of kilometers in size. The process of accretion, where these planetesimals merge under their own gravity, leads to the formation of protoplanets. The location of a forming planet within the disk plays a crucial role in determining its composition and characteristics. Close to the star, where temperatures are high, only materials with high melting points, such as metals and silicates, can condense. This region gives rise to rocky terrestrial planets like Earth and Mars. Farther from the star, beyond the frost line, temperatures are low enough for volatile compounds like water, methane, and ammonia to freeze into ice. In these regions, planets accumulate vast amounts of icy material, forming the cores of gas giants and icy worlds. The interaction between forming planets and the protoplanetary disk shapes the architecture of planetary systems. Gas and dust in the disk exert gravitational forces on the planets, causing them to migrate. This migration can move planets closer to or farther from their star, dramatically altering their orbits. Hot Jupiters, for example, are thought to have formed beyond the frost line, but migrated inward to scorchingly close orbits. This phenomenon underscores the dynamic nature of planetary systems, where no orbit is guaranteed to remain static. Planets also influence the disks from which they form. Massive planets can carve gaps in the disk, creating distinct rings and structures visible in observations. These interactions reveal the presence of planets long before they can be directly detected, offering indirect evidence of their formation. Observations of protoplanetary disks by telescopes like ALMA Atacama Large Millimeter/Submillimeter Array, have provided stunning images of these features, highlighting the intricate interplay between planets and their birth environments. As planets grow, their composition evolves through processes such as differentiation, where denser materials sink to form cores and lighter materials rise to create mantles and atmospheres. These processes influence a planet's geology, magnetic field, and ability to retain an atmosphere, all factors critical to its potential for habitability. For gas giants, the accumulation of hydrogen and helium from the disk determines their final sizes and compositions, setting them apart from rocky and icy worlds. The eventual dispersal of the protoplanetary disk marks the end of planet formation, but not the end of a planet's evolution. Stellar winds and radiation gradually blow away the remaining gas and dust, leaving behind fully formed planets and debris. What remains is a planetary system, where gravitational interactions continue to shape the fates of its members. Collisions between leftover planetesimals can create moons, as in the case of Earth's moon, or even trigger the ejection of planets, resulting in rogue worlds wandering the galaxy. Studying planet formation is not merely an exercise in understanding the past. It provides a foundation for interpreting the present. By comparing observed exoplanets to theoretical models, astronomers can refine their understanding of how planets form and why they take on such diverse forms. The discovery of super-Earths, mini-Neptunes, and other types of exoplanets has challenged existing models, prompting new theories about the role of migration, discomposition, and stellar influences. Looking to the future, missions like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope will enhance our ability to study young planetary systems and protoplanetary disks. These tools will allow scientists to observe the earliest stages of planet formation, capturing snapshots of planets as they emerge from their birthplaces. Combined with ground-based observatories and next-generation instruments, these missions will continue to unveil the secrets of planetary creation. Planet formation is a story of transformation, where chaos gives rise to order, and the interplay of forces creates worlds of extraordinary diversity. It is a process that connects us to the cosmos, reminding us that our planet, too, emerged from the remnants of a molecular cloud, shaped by the same forces that govern the universe. As we explore the origins of planets, we deepen our understanding of the forces that make them possible and the myriad forms they can take. Exoplanets is not only one of discovery, but also of understanding the intricate relationships between planets, stars, and the broader cosmic environment. At the center of every planetary system is a star, the source of energy, light, and often life-sustaining conditions. The interaction between a star and its orbiting planets defines the character of the system, influencing everything from planetary climates to atmospheric compositions and orbital dynamics. Stars provide the energy that shapes planetary environments. For rocky worlds in the habitable zone, stellar light regulates surface temperatures, driving weather patterns, water cycles, and potentially even biological processes. The type of star significantly affects these dynamics. Sun-like stars, for instance, offer stable, long-lived environments conducive to the development of complex ecosystems. In contrast, red dwarfs, though smaller and cooler, often emit intense flares and ultraviolet radiation that can strip away planetary atmospheres or alter their chemistry, posing challenges for habitability. The size, temperature, and activity of a star also determine the boundaries of its habitable zone. For smaller, cooler stars like M dwarfs, the habitable zone lies much closer to the star, creating unique challenges for planets in this region. Planets close to their stars are often tidally locked, with one side perpetually facing the star and the other shrouded in darkness. This dichotomy can create extreme climate conditions, with scorching temperatures on the day side and freezing conditions on the night side. However, atmospheric circulation might mitigate these extremes, potentially making tidally locked planets viable candidates for habitability. In more massive stars, the habitable zone is located farther out, but the star's short lifespan often limits the time available for life to develop. O and B-type stars, for example, burn through their fuel rapidly, leaving little opportunity for complex ecosystems to emerge on their planets. This makes planets around smaller, longer-lived stars like K-dwarfs particularly intriguing for the search for life, as they combine stable conditions with extended time frames for biological evolution. The interaction between planets and their stars extends beyond energy and light. Stellar winds, composed of charged particles streaming from the star, can strip away a planet's atmosphere, particularly if the planet lacks a strong magnetic field. These interactions are most pronounced in close-in planets like hot Jupiters, where intense stellar radiation and winds can erode gaseous envelopes over time. Observations of these processes, such as the atmospheric escape detected in HD 209458b, provide critical insights into the long-term evolution of planetary systems. Stellar activity also plays a role in shaping the chemistry of planetary atmospheres. Ultraviolet radiation from the star can break apart molecules, triggering chemical reactions that alter the composition of the atmosphere. These processes can create or destroy potential biosignatures, complicating efforts to identify signs of life. For example, oxygen might accumulate abiotically on planets orbiting active red dwarfs, creating a false positive for biological activity. Beyond individual star-planet interactions, the broader environment of a planetary system also influences its development. Stellar companions in binary or multi-star systems can destabilize orbits, induce migration, or even eject planets from the system entirely. Conversely, gravitational interactions with a secondary star can shepherd material in protoplanetary disks, enhancing planet formation in certain regions. The interplay between these forces adds layers of complexity to planetary systems, revealing a diversity of outcomes far beyond what is seen in our solar system. The study of star-planet interactions is crucial for understanding the potential for life beyond Earth. By examining how different types of stars influence their planets, scientists can refine the criteria for habitability and identify the most promising targets for future exploration. Instruments like the James Webb Space Telescope are already providing detailed observations of star-planet systems, analyzing the effects of stellar radiation on planetary atmospheres, and searching for signs of chemical equilibrium or disequilibrium that might indicate life. Future missions will take this research even further. Projects like LUVOIR and HabEx aim to directly image Earth-like planets around nearby stars, providing unprecedented detail about their atmospheres and surfaces. These missions will not only search for biosignatures, but also investigate the broader effects of stellar environments on planetary systems, from the stability of orbits to the persistence of water and other life-sustaining elements. The relationship between stars and planets is a testament to the interconnectedness of the cosmos. Stars shape the conditions under which planets form, evolve, and potentially support life. In turn, planets reflect the history and character of their stars, bearing the imprints of their stellar environments. By studying these relationships, we gain not only a deeper understanding of exoplanets, but also a richer appreciation for the forces that shape our universe. The journey to understand exoplanets is deeply intertwined with the tools and technologies we use to observe them. The field of exoplanetary science, which has grown from speculation to one of the most dynamic areas of astronomy, owes much of its progress to the development of increasingly sophisticated instruments. These tools, from ground-based telescopes to cutting-edge space observatories, serve as our eyes in the universe, enabling discoveries that redefine our understanding of planetary systems. Ground-based telescopes have long been the backbone of astronomical observation. Located in remote, high-altitude sites to minimize atmospheric interference, these telescopes have played a pivotal role in detecting and characterizing exoplanets. Instruments like the High-Accuracy Radial Velocity Planet Searcher, HARPS, mounted on the European Southern Observatory's 3.6-meter telescope in Chile, have been instrumental in discovering planets through the radial velocity method. By detecting the tiny wobbles in a star's motion caused by an orbiting planet, HARPS and similar spectrographs have identified hundreds of exoplanets, including many small, rocky worlds. While ground-based telescopes excel in certain areas, they face inherent limitations due to Earth's atmosphere. Atmospheric turbulence blurs observations, a phenomenon known as seeing, which limits the precision of measurements. Adaptive optics, a technology that uses deformable mirrors to counteract atmospheric distortions in real time, has significantly improved the resolution of ground-based observations. This innovation allows telescopes like the Very Large Telescope (VLT) in Chile and the Keck Observatory in Hawaii to capture sharper images and perform more detailed studies of exoplanetary systems. Despite these advancements, some aspects of exoplanet science can only be addressed by escaping Earth's atmosphere entirely. Space-based telescopes provide a pristine view of the cosmos, free from atmospheric distortion and absorption. These observatories have revolutionized our ability to detect and study exoplanets, with missions like Kepler, TESS, and the James Webb Space Telescope leading the charge. The Kepler Space Telescope, launched in 2009, was a game-changer in the field. By monitoring the brightness of over 150,000 stars, Kepler identified thousands of exoplanets using the transit method, where a planet passing in front of its star causes a slight dip in brightness. Kepler's discoveries revealed the extraordinary diversity of exoplanets, from compact systems with multiple Earth-sized planets to exotic worlds with orbits and compositions unlike anything in our solar system. The telescope also provided the first statistical evidence that planets are ubiquitous, with nearly every star in the galaxy likely hosting at least one. Building on Kepler's legacy, the Transiting Exoplanet Survey Satellite, TESS, expanded the search for exoplanets to nearly the entire sky. TESS focuses on stars closer to Earth, enabling follow-up studies with ground-based telescopes and future missions. Its discoveries include small, rocky planets in the habitable zones of their stars, prime candidates for atmospheric characterization and the search for biosignatures. The James Webb Space Telescope (JWST), launched in 2021, represents a new era in exoplanet research. With its ability to observe in the infrared spectrum, JWST is uniquely suited to studying the atmospheres of exoplanets. Its instruments can detect water vapor, carbon dioxide, methane, and other key molecules, providing insights into the potential habitability of distant worlds. For gas giants, JWST is revealing the compositions and dynamics of their thick atmospheres, while for rocky planets, it is analyzing surface conditions and searching for signs of biological activity. Future missions promise to push the boundaries even further. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will use a wide-field survey approach to discover and characterize exoplanets, including through direct imaging. Direct imaging, one of the most challenging techniques, involves capturing actual pictures of planets by blocking out the overwhelming glare of their host stars. This method requires advanced technologies like coronagraphs and star shades, which will enable the study of planets' surfaces and atmospheres in unprecedented detail. Concepts for the next generation of observatories, such as LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, aim to detect and study Earth-like planets around nearby stars. These missions would combine direct imaging with spectroscopic analysis, searching for biosignatures and exploring the potential for life beyond Earth. Their ambitious goals include identifying planets that resemble our own in both size and atmospheric composition, taking the search for extraterrestrial life to the next level. In addition to dedicated exoplanet missions, general-purpose observatories like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have made significant contributions. Hubble's ability to observe ultraviolet and visible light has been critical for studying the atmospheres of transiting exoplanets, while ALMA's sensitivity to millimeter wavelengths has provided insights into protoplanetary disks and the early stages of planet formation. As the field advances, emerging technologies promise to enhance our capabilities even further. Artificial intelligence and machine learning are playing increasingly important roles in data analysis, enabling the detection of subtle signals that might otherwise go unnoticed. Quantum sensors and interferometry techniques are being explored for their potential to achieve even greater precision in measurements. The synergy between ground-based and space-based observations, combined with advancements in technology, ensures that the study of exoplanets will continue to thrive. Each new instrument and mission brings us closer to answering profound questions about the nature of planetary systems and the possibility of life elsewhere in the universe. These tools, born of human ingenuity, are not just instruments of discovery. They are extensions of our curiosity, reaching across the cosmos to uncover its secrets. As our understanding of exoplanets deepens, the study of their atmospheres emerges as a critical avenue for exploring their nature, history, and potential habitability. Atmospheres, the gaseous envelopes surrounding planets, hold key information about a planet's composition, climate, and even its capacity to support life. Through the analysis of light interacting with these atmospheres, astronomers can decode the stories of distant worlds, unveiling details that were once beyond our reach. Atmospheres serve as both protectors and mirrors of their planets. On Earth, our atmosphere regulates temperature, shields the surface from harmful radiation, and provides the essential gases for life. On exoplanets, atmospheres perform similar roles, though their compositions and dynamics can vary dramatically. These variations offer insights into planetary formation, evolution, and the interactions between planets and their stellar environments. The study of exoplanetary atmospheres begins with the detection of specific molecules. When light from a star passes through a planet's atmosphere during a transit, some wavelengths are absorbed by atmospheric gases. This creates a unique spectral fingerprint, allowing scientists to identify the presence of molecules such as water vapor, carbon dioxide, methane, and oxygen. These molecules provide clues about the planet's temperature, pressure, and chemical processes. Transmission spectroscopy, the technique used to analyze light filtered through an atmosphere, has been one of the most productive tools in this field. By observing the changes in a star's light as a planet passes in front of it, astronomers can infer the composition and structure of the atmosphere. This method has been particularly successful for gas giants, where thick atmospheres create pronounced spectral features. For example, the atmospheres of hot Jupiters often show evidence of water vapor, sodium, and other elements, providing insights into their dynamic and hostile climates. For smaller, rocky planets, atmospheric studies are more challenging. Their thin atmospheres create weaker spectral signals, requiring highly sensitive instruments like those on the James Webb Space Telescope. Despite these challenges, observations of planets like TRAPPIST-1e and LHS-1140b are beginning to reveal the atmospheric compositions of potentially habitable worlds. Detecting biosignatures, chemical markers of life, such as oxygen-methane disequilibrium, on such planets remains a primary goal of atmospheric studies. One of the most exciting aspects of atmospheric research is its potential to identify signs of habitability or even life. Water vapor, for instance, indicates the presence of liquid water under the right conditions. Methane, when found alongside oxygen, suggests biological activity, since these gases would typically react and neutralize each other in the absence of a replenishing source. Detecting these combinations could provide indirect evidence of life on distant planets. Atmospheres are also windows into planetary history. The composition and structure of an atmosphere reflect the processes that have shaped a planet over time. For example, the loss of lighter gases due to stellar radiation reveals insights into the planet's gravitational strength and magnetic field. Similarly, the presence of volcanic gases, such as sulfur dioxide, points to ongoing geological activity that can influence climate and habitability. Extreme planetary environments offer some of the most fascinating atmospheric phenomena. On ultra-hot Jupiters, temperatures can exceed 2000 Kelvin, creating conditions where metals like iron and titanium vaporize. These planets exhibit thermal inversions, where the upper atmosphere is hotter than the lower layers, driven by the absorption of stellar radiation by high-altitude compounds. Observing these exotic worlds not only reveals the chemistry of extreme climates, but also challenges our understanding of atmospheric physics. The study of exoplanetary atmospheres also extends to processes like atmospheric escape. Intense stellar radiation and winds can strip away a planet's atmosphere, particularly for those orbiting close to their stars. This phenomenon has been observed in planets like HD 209458b, where hydrogen gas forms a trailing cloud as it escapes the planet's gravitational pull. Understanding atmospheric escape helps refine models of planetary evolution and the conditions necessary for a planet to retain its atmosphere. Clouds and hazes add complexity to atmospheric studies. On Earth, clouds play a critical role in climate regulation, reflecting sunlight and distributing heat. On exoplanets, Clouds composed of exotic materials like silicates and iron can obscure spectral signals, complicating efforts to analyze atmospheres. However, they also offer valuable information about the planet's temperature and chemical processes, providing indirect clues about atmospheric dynamics. The future of atmospheric studies lies in the advancement of technology and observational techniques. Instruments like the James Webb Space Telescope are already providing unprecedented insights, while upcoming missions like aerial, atmospheric remote sensing, infrared exoplanet large survey will focus specifically on characterizing exoplanet atmospheres. These missions aim to analyze the atmospheres of hundreds of planets, creating a comprehensive catalog of atmospheric compositions and properties. Direct imaging, a technique that isolates the light from a planet from its host star, represents another frontier in atmospheric studies. By capturing and analyzing light emitted or reflected by a planet, astronomers can study its atmosphere without relying on transits. This approach is particularly valuable for planets that do not align perfectly with their stars from our perspective. As atmospheric studies advance, the line between science fiction and reality continues to blur. The ability to analyze the skies of distant worlds, searching for hints of alien weather or life, represents a profound leap in our understanding of the universe. Each new discovery brings us closer to answering the ultimate questions about our place in the cosmos and the potential for life beyond Earth. The search for exoplanets and their atmospheric compositions is not just a scientific endeavor. It is a profound exploration of the conditions that might lead to life. Among the many factors that influence planetary environments, one of the most crucial is the concept of equilibrium and disequilibrium within a planet's atmosphere. These states, shaped by physical, chemical, and biological processes, provide key insights into the nature of distant worlds and the possibility of life existing on them. Atmospheric equilibrium occurs when a planet's atmosphere is in a stable state, where chemical reactions proceed at rates that maintain a consistent composition over time. For example, on a planet with no life, elements like carbon dioxide, methane, and water vapor might exist in ratios determined solely by geophysical and photochemical processes. In such cases, the atmosphere reflects the balance of these forces, and its composition remains relatively static unless disrupted by external factors, such as volcanic activity or stellar radiation. Disequilibrium, by contrast, is a state where certain gases coexist in ratios that are not chemically stable over long periods without an active replenishment mechanism. On Earth, the coexistence of oxygen and methane in the atmosphere is a classic example of disequilibrium. These gases naturally react to form carbon dioxide and water, yet they persist due to the continuous production of oxygen by photosynthetic organisms and methane by biological and geological processes. This persistent imbalance is one of the strongest indicators of active life on Earth. The search for atmospheric disequilibrium on exoplanets is therefore a cornerstone of astrobiology. When analyzing the atmospheres of distant worlds, scientists look for combinations of gases that cannot easily be explained by abiotic processes alone. For example, the simultaneous presence of large amounts of oxygen, methane, and water vapor would be challenging to sustain without biological activity. Detecting such a combination would provide compelling evidence for life, or at least processes analogous to those driven by life on Earth. While disequilibrium is a powerful tool in the search for life, it is not without challenges. Many non-biological processes can also produce atmospheric imbalances. For instance, volcanic activity can release methane, and photodissociation caused by stellar ultraviolet light can generate oxygen. Distinguishing between these abiotic processes and potential biosignatures requires a deep understanding of the planet's broader context, including its geology, climate, and stellar environment. The role of the host star is particularly significant in shaping atmospheric chemistry. Stars emit radiation across a spectrum of wavelengths, influencing the photochemistry of their planet's atmospheres. M-dwarf stars, for example, produce high levels of ultraviolet radiation, which can break down water molecules into oxygen and hydrogen. This process might lead to an oxygen-rich atmosphere without the presence of life, a phenomenon that complicates the interpretation of oxygen as a biosignature. The detection of disequilibrium also depends on the sensitivity of observational tools. Instruments like the James Webb Space Telescope are designed to analyze the light passing through or reflected by a planet's atmosphere, capturing the spectral fingerprints of various gases. These observations provide snapshots of atmospheric composition, but achieving a complete picture requires multiple observations over time, especially to detect transient phenomena like volcanic eruptions or atmospheric escape. In addition to identifying disequilibrium, scientists are also exploring the concept of superhabitable conditions, where planets or moons might offer environments even more conducive to life than Earth. Such conditions might include an atmosphere with a balanced greenhouse effect, moderate surface gravity, and a stable climate sustained by geochemical cycles. These factors create a sweet spot where disequilibrium driven by life could persist for billions of years, allowing complex ecosystems to emerge and evolve. The potential for disequilibrium extends beyond planets to include moons. Large moons orbiting gas giants may experience tidal heating, which can drive geological activity and sustain atmospheres. Europa and Enceladus in our solar system are prime examples, with subsurface oceans that might support microbial ecosystems. Exomoons with similar conditions could exhibit atmospheric disequilibrium, offering additional avenues in the search for life. The implications of discovering disequilibrium on an exoplanet are profound. Such a finding would not only suggest the presence of active processes, but also raise fundamental questions about the nature of life in the universe. Would extraterrestrial life share biochemical similarities with Earth organisms, or would it rely on entirely different mechanisms? Could we detect it? And if so, how would its discovery shape our understanding of biology and the origins of life? Beyond the search for life, studying equilibrium and disequilibrium helps scientists refine models of planetary evolution. By understanding the balance of forces that shape atmospheres, we gain insights into how planets form, how they sustain climates, and how they transition over time. These insights are critical for interpreting the vast diversity of exoplanets and for understanding the conditions that led to Earth's own habitability. Disequilibrium represents the dynamic, ever-changing nature of planets and their atmospheres. It is a phenomenon that bridges the fields of physics, chemistry, and biology, revealing the intricate connections between a planet's internal processes and its external environment. As we continue to explore the cosmos, the search for disequilibrium will remain at the forefront of our efforts to uncover the secrets of life and the forces that shape the universe. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.